Okay, so welcome to our morning session of Monday. Today we have Don Salisbury, who will talk about algebraic quantum field theory. Don, go ahead.
Yes, okay. Thank you so much. I really feel this is a privilege and an honor to be able to address you folks. And I'm so sorry that I was unable to be there in person, because I had been looking forward to continuing conversations. So I'm going to talk about field-dependent general covariance and its likely conflict with algebraic quantum field theory. Unfortunately, I'm not going to be able to provide answers to the questions that I will be posing. And in fact, let me go next directly to, how do I change my page? Sorry, there it goes. So just a brief overview of what I intend to talk about. So first introduction, but then I'm going to do some history. In fact, much of this talk is going to be concerned with recent historical investigations that I've carried through and published, beginning actually with Cartan in 1922 and proceeding with Weiss and Swinger. But then I want to address the Dirac algebra that in fact incorporates this field dependence, which I perceive as a problem. Then I'm going to talk a bit about some recent work I've done in analyzing Peter Bergman's and Art Kolmar's work on Hamilton-Jacobi approaches to general relativity. And then finally, at the end, I will try to at least pose this question of the conflicts that I perceive arising in this context. Of course, I also welcome any questions or objections along the way, so you should feel free to do so. So what I really intend to do here is to give, as I said, an historical overview and focusing in particular on work that Peter Bergman and his Syracuse group undertook. In this case, mainly in the 1950s, 1960s, early 1970s. In fact, when we get as far as the late 1970s, we get to my own PhD work under Peter's direction, which I completed in Syracuse in 1977. I do want to mention here that Ball actually played an important role in this thesis that I undertook under Peter's direction. I don't recall whether it was Ball or it was Fritz Rohrlich who suggested to Peter that the relativistic string would be an appropriate model to quantize because of its underlying general covariance, or in this case, general reparameterization covariance. And Ball really helped me a lot in preparing to undertake this project. I learned a lot of Virasoro algebra from him, and I'm grateful for that. I do want to say also that I regret that I have not, in the recent past, been following as carefully as I wish I had the work of Ball and so many of his collaborators. It's a really massive collection of important papers. And in fact, I tried to participate in the 316 meeting again recently, and I will try even harder in the future. I've begun to really look more carefully at much of this literature. I wish I had done so in the past. So let me go on to the Cartan formalism. So Cartan's idea was that one could reformulate the laws of classical mechanics, in this case, so with a finite number of variables, by posing this requirement that one begin with a Lagrangian with, can you see it as I move my cursor across the page? Anyone there? Up? Can anyone respond?
No, he can't, yeah.
Oh, you can't see that?
No, we can't.
Okay, so I'm looking at the variables Q and V in the Lagrangian. In the Cartan approach, these were taken to be independent functions of time. And then one constructed a closed interval in the parameter S such that when one went through the range, S goes from 0 to 1, one actually returned back to the original values of the Q variables and also the V variables. And so Cartan posed this invariant integral request. He said, let's require that this object remain invariant under arbitrary variations of the Q's and the V's, and also the time in this case. So they were all supposed to be parameterized by this parameter S. So he required that this closed interval over S be independent of these variations. And in fact, this immediately delivered the Euler-Lagrange equations. So this was really an important new development, which has since then taken various different important forms. So let me go on here to, of course, the expression, the first in that integral was the usual one form, P dq. That actually was attributed to Poincaré. It's called the Poincaré one form, but then Cartan's idea was to extend this to include the Hamiltonian and increments in the time itself. So this is now called the Poincaré Cartan one form. I want to, in particular, mention here that one thing that Cartan could do very quickly in this formalism was show that one could very quickly derive the Hamilton-Jacobi equations from the use of this invariant integral. So one could require that little p, little dq, and capital P, capital dq, and the corresponding Hamiltonians for whatever model one was considering could be written as the differential of another function, capital G of little q and capital Q. And when one does that, in fact, when one requires that K itself is 0, then one immediately gets to this Hamilton-Jacobi approach, in which case, since the Hamiltonian is 0, one is dealing with constants of the motion, which I'm calling here beta and alpha. And then it's straightforward to show, as I have on this slide, that the result of this change of canonical variables is the usual Hamilton-Jacobi equations. So the momentum is written as the partial of the action with respect to Q, and then one has the usual Hamilton-Jacobi equation. Of course, one additional wonderful result from this formalism is that then one can set beta equal to a partial of S with respect to these constants, and then from there actually derive the full set of solutions of the classical Euler-Lagrange equations. Okay, so let me go on to Weiss's extension. He actually decided to try to extend the Cartan formalism to field theory. And it's interesting that he was actually a student of Max Born in Germany, but then Born went to England, and in 1936 moved from Cambridge to Edinburgh, and Paul Dirac became Paul Weiss's director. So I think that link is important between Weiss, Dirac, and others, as we shall see. So what Weiss did then was to pioneer this new approach based, in fact, on the Poincaré-Cartan increment. He extended it to field theory. And so the idea was, he did this because he wanted to ensure Lorentz covariance of this formalism. The idea was that he would do this formulation on arbitrary space-like surfaces, which I've indicated here are parameterized by parameter W, which is in time-length direction actually, and its 3 parameters U. And then one object which plays an important role in this formalism is the normal, in this case, the covariant normal to whatever surface Weiss chose in which to formulate this extended Cartan principle. So I mention this in particular because, well, first of all, Schwinger himself expressed his own debt to Dirac in his own formulation, his quantum action principle, which indeed was related to Weiss's work. But Dirac never mentioned Weiss, as far as I can tell, in any of his work, although, but he did refer to Dirac, and Dirac did refer to Weiss in his 1948 important paper on the covariant formulation of quantum electrodynamics. Okay, so Weiss defined a complete variation in which both the fields phi and the space-time coordinates are varied. And then he required, as did Cartan, that these variations lead to new solutions of the dynamical equations, which again we can suppose are labeled by this parameter S, which also in this case could run through a range from 0 to 1, in which case leading back to the original values and leading back, if one wished, to this Cartan invariant integral approach. Now, one important object which appears here, of course, is the increment in the field itself, which I've labeled by phi sub alpha. There are indeed two variations present here, one in the field and the other in the coordinates, in this case, the 4 coordinates, not just the time. And this leads to a variation at fixed space-time coordinates, which is given by this bottom expression for d naught, alpha, phi sub alpha. So this is an object which plays an important role in Weiss's formalism, but of course also in the formalism of Dirac. Okay. So then one looks at variations about solutions, and the requirement is that these variations. Yes.
John, can you click? There's some boxes appearing in front of your thing. Can you? Yeah.
So what?
Yeah. Okay. And close that window. Thank
you. Is it okay now?
It's good.
Okay. Good. Okay. So I go to the next page. Good. Okay. All right. So so the idea here is that now one wants to require that this increment in the action, provided the equations of motions are satisfied. And I should have pointed out earlier, of course, I'm throughout here I'm looking at the classical formalism and not the quantum formalism. So one indeed requires that the increment in action should be given by the difference between these three-dimensional integrals over these arbitrary space-like surfaces. So they're labeled by the variables sigma 2 and sigma 1. I've given you below the definitions of the momenta conjugate to the phis that appear here, and also the momenta that appear conjugate to the x variables. Of course, the naught variable here is in fact just the Hamiltonian in this arbitrary formalism. It is interesting that Peter Bergman also did refer to Weiss's paper in some of his early work dealing with reparameterization, covariant field theory. But Bergman indeed did require the full covariance, the Hamiltonian covariance of his model, and Weiss did not. So the next step here in this history is Schwinger's own action principle, but now, of course, stated in terms of quantum operators. I have noticed that although I think this had not been adequately appreciated in the past, that several of you folks there have referred here to the Cartan-Weiss principle, and I think that's quite appropriate because I think Weiss did play an important role in the development of Schwinger's own quantum action principle. So, so I'm simply rewriting here the variations that Schwinger invoked, but of course now in terms of quantum operators. And I don't go through the details of this here, but of course what he was able to show was that ultimately the phi and the pi's turned out to be conjugate variables within this formalism. Okay, so one thing that Weiss did, and Schwinger also did this carefully, was recommended how to deal with the underlying gauge symmetry in quantum electrodynamics. Schwinger's important step was to assume that the F mu nus and the A's were independent. In fact, it turns out that this was in fact an important lead that was used by Arnold, Dazer, and Misner in their original treatment of general relativity. But I'm not going to be able to go into that history in detail in this talk, of course. But there is one thing that I want to say here, that even though Schwinger did not make this observation in his original papers, that it does turn out that what he was doing was dealing with an underlying fiber bundle structure, and I think that's something I'm going to give an important role in what follows. So let me go now to Dirac and Bergman, and an individual that you may not be familiar with, T.S. Chang. And I'll explain why I'm doing that here. So I have claimed that Dirac did benefit from Weiss's arbitrary Minkowski space-like surface approach in his 1948 paper dealing with localized quantum systems. And in that paper in 1948, the normal vector does play a decisive role. And also the induced 3 metric appears explicitly in the resulting surface deformation algebra. So in the Dirac formalism. So indeed, in Dirac's formalism, and again, I want to stress this deals with arbitrary space-like surfaces in flat Minkowski space. But he dealt with variations which were perpendicular to the surface and variations which are tangential to it. I think it has not been adequately appreciated that T.S. Chang was certainly engaged in conversations with Dirac. Chang actually got his PhD at Cambridge in the mid-30s. He actually was able to return to Cambridge after the end of World War II. And he was acquainted, of course, very well with Dirac. And when he came back to Cambridge in 1948, or actually it was 1947, Chang actually accompanied Dirac to the Institute for Advanced Study in Princeton. And it is certain that he actually engaged in conversations with Dirac at that stage. I mention this here because it's only recently been discovered, and actually it was pointed out by one of my former collaborators, Yin Xiaodong, that Chang himself had been working on this algebra, which involved the use of this normal to the space-like surface. And in fact, he actually drafted his own paper on this, not being aware that Dirac himself was also writing such a paper. But by this time, Chang was in China, and he didn't learn about Dirac's paper until after he had already written his own draft. But I suspect that Chang was deeply involved. I think also probably because Chang himself had been in contact and was a acquaintance and a conversation partner with Paul Weiss himself. So why is all of this important? Well, it's important in my opinion because Dirac had realized that there was a problem in trying to implement full 4-dimensional diffeomorphism covariance in the Hamiltonian formalism well, in the original case, this was in the formalism of fields on curved surfaces in flat space-time. But Bergman found, and apparently he was the first to actually have pointed this out, that what Dirac actually accomplished here was something of a miracle because as Bergman pointed out, one looks at the usual Lie algebra of infinitesimal diffeomorphisms in space-time, so in this case in curved space-time, then one arrives at time derivatives of the descriptors of these infinitesimal transformations. And of course, if one looks at commutators of these transformations, then one gets higher and higher time derivatives of these descriptors. And that means that this process is simply not realizable in a phase-space formalism of general relativity, since one has these additional time derivatives that appear. And I think my own view here is that Bergman was the first to have recognized that Dirac had made this important contribution. And Bergman, in fact, was the first to have written down the full variation that resulted from assuming that one deals with field-dependent infinitesimal transformations, which depend on the normal to the space-like surface. And this normal is represented by n super mu. In current terminology, that normal is expressible in terms of the lapse and shift functions in general relativity. And Bergman was the first in 1962 to derive the corresponding algebra. And the crucial observation here is that in this algebra, the inverse to the three-dimensional metric appears within the algebra. Of course, this led everyone to say, well, this is no longer a true commutator algebra because one had this mandatory field dependence. And this mandatory field dependence is, of course, something that I'm placing great stress on, as I have in previous presentations at Paul's meetings, and I suspect that you're probably, some of you, becoming tired of hearing this story, but I really would like to instigate some conversation on this puzzle, this topic. As far as I can tell, Dirac never wrote down the crucial commutator that applied to the general relativistic case. And as far as I can tell, it was Bryce DeWitt who first wrote this out I think it was in 1967 in a series of papers. And again, we see here that in this commutator of the H0 constraint in Hamiltonian general relativity, it's the 3 metric that appears in this commutator. So what do we do with this is the question. Now, of course, this is not the full story. It turns out, and this is something I've discussed with many of you folks before, it turns out that the full 4-dimensional diffeomorphism covariance is still present in the Hamiltonian formulation of general relativity. But in order to implement it, one has to retain the lapse and shift as canonical variables. And then one is able to derive the full infinitesimal generator of transformations which are written in terms of the normal and attention to the hypersurface. As you see here, the full generator, which I call G script sub psi, is written in terms of primary constraints. The P sub A are, in fact, the primary constraints that result from the absence of time derivatives of the lapse and shift functions. And the C's here are the structure functions that appear in the Poisson brackets amongst these constraints. We actually, one of the first derivations of this full generator, I and my collaborators completed in 1997. Of course, that derivation was based upon a group theoretical-based approach. I'll say a little bit more about this in a moment, but of course, once one has this full generator, then one is able to write down the complete generator for finite diffeomorphisms. And of course, one is still doing this within the classical formalism. The question is, how indeed could one apply this formalism to the quantum theory? Again, I've stressed already that the lapse and the shift have to be retained as canonical variables within this formalism. And I think it's also not adequately appreciated that this classical general relativistic formalism is fully covariant under time new time foliations. Those new foliations involve simply these new multipliers that appear in the full generator. So, at least at the classical level, it's possible to retain the full four-dimensional diffeomorphism covariance. But this leads to some problems, and this is the question that I really wanted to address here and hopefully try to instigate a conversation. Bergman himself noted in a 1976 paper, referring to this metric-dependent covariance group. Of course, at that stage, he himself also did not have the full group at his disposal, but nevertheless, he did make, and I'll quote here, make this remark, that these transformations, foremost among them canonical transformations, do not map fiber on fiber or world point on world point. The projective mapping that relates the bundle manifold to the base manifold is lost. Under these circumstances, the fiber bundle becomes unwieldy. And he added later, there is no simple relationship between Dirac's phase space and fiber bundles over the space-time manifold. And interestingly here, he acknowledges conversations that he'd held at that time with Andre Trautmann. And I might also point out another article that is worth looking at, short one, called The Fading World Point, which again has to do with this disappearance of the fiber bundle approach in trying to implement this full four-dimensional diffeomorphism covariance. I might also add here, I found this kind of interesting that I had actually given this talk on this full four-dimensional diffeomorphism covariance in Poland with Andre Trautmann. And he did express to me his own concern over the applicability of the fiber bundle approach in light of this metric field dependence that appears in this diffeomorphism symmetry. And you might look, we didn't address this question directly in this paper that we published. This actually is an account of an interview which I did with Andre Trautmann, I think it was in 2016. I think most of you are familiar with the significant role that Trautmann played in promoting fiber bundle approach in general. So let me talk a bit about the Bergman and Komar approach. Let's see, I think I'm going to manage to do this in 35 minutes. I keep time here. So I do want to tell you a little bit about what Bergman and Komar themselves did in relationship to the Hamilton-Jacobi approach to general relativity. I've just recently published an article in the European Physical Journal H, which about this Hamilton-Jacobi history, incorporating actually much of the discussion that I've given you earlier about the roles of Cartan, Weiss, and Schwinger, and ADM, and Kugach. But I'm afraid I can't go into that in detail here. So one thing I do want to mention here, that Bergman very early on strenuously objected to Wheeler's disregard of the full four-dimensional diffeomorphism symmetry. And there was a debate between Bergman and Wheeler on one of the foundation principles of Wheeler's geometric dynamics program. The centerpiece of this program was Wheeler's identification of three geometries. as legitimate observables in his action-based approach. But when I say three geometries here, I do recognize that Wheeler did implement the three-dimensional diffeomorphism symmetries, but not the four-dimensional. In fact, Wheeler and DeWitt and others discounted this full four-dimensional symmetry and replaced it by a notion of multi-fingered time. And I think this is a notion that is dominant still within this field. And I noticed that, at least in some of Bal's earlier papers with many of his collaborators, reference is made to the H0 as implementing time reparameterizations with no mention of the full four-dimensional symmetry that needs to be invoked, I believe, in passing from classical general relativity to quantum gravity.
Don, you have 10 minutes? 10 minutes.
10 minutes?
Yeah.
Good. I think I'm going to make it. Okay, good.
Okay.
So another thing I thought was interesting here is I think it's not fully appreciated that the role that Bergman himself played in what became known as the Wheeler-DeWitt approach to general relativity. Of course, Wheeler and DeWitt were referring to the Hamilton-Jacobi equation, which results from simply replacing the momenta that appear within the H0 constrained by functional derivative with respect to the three metric. But I think it's not adequately recognized that it was Bergman who pointed out to Perez that his introduction of this functional came from a Hamilton-Jacobi approach to the gravitational field. Now, just a few words then about what Bergman and Komar did in their own Hamilton-Jacobi approach. First, Bergman was able to show, for a finite dimensional system, that the resulting solution for S could not depend explicitly on the coordinate time. And Komar extended that analysis, in fact, actually attributing it to Bergman, to general relativity, and showing that when one dealt with this system of four so-called Wheeler-DeWitt equations, the resulting S that appears here could also not depend on the spatial coordinates. But one thing that Komar did in particular, and I think this is an important development, is he actually decided that in order to fix the three momenta, one needed to add two more Hamilton-Jacobi equations. This effectively amounts to imposing gauge conditions. And then he was able to work out that the solutions of these 6 Hamilton-Jacobi equations could be characterized by diffeomorphism invariants, which I've called here these functions alpha sub a. They are indeed invariant under the full four-dimensional diffeomorphism group. And furthermore, Komar was able to show that there were variables conjugate to these alphas also invariants. And then in making use of these variables, assuming one was able actually to solve these 6 Hamilton-Jacobi equations, one could in principle obtain the full list of solutions of physically inequivalent solutions of Einstein's equations by setting beta equal to the functional derivative of S with respect to this alpha. So this is work which was done in the late 60s and early 70s. So question is, what happened to space and time here? And I've talked to many of you about this previously, and I just want to briefly mention here that the proposal that I and my collaborators have been pursuing is to fix a gauge by setting the space-time coordinates x super mu equal to appropriate functions of the Weyl scalars. So the x mu then actually become functions of these phase space variables, and that would imply some appropriate approach to quantum gravity that they would become operators. I also want to mention here that I have some collaborators now, actually at Baylor University, who are currently constructing a perturbative mathematical procedure for identifying appropriate candidates for these space-time coordinates. So in nearly flat space-times. So unfortunately, I can't report on complete results that we have to date, but the results look promising. I also want to mention here that I did, for BalFest, I did expand this Cartan invariant integral approach to Einstein-Yang-Mills theory. And also, I used a new approach to develop the corresponding generator of a mixture of general coordinate invariance with gauge invariance. And I had hoped to be able to make some progress in doing the same thing with the Holst, Barbero-Immersi Lagrangian, but I'm afraid that is still an ongoing project. But again, I really look forward to conversations. So, apparently, what's the problem here?
5 minutes.
Okay, good. This is very quick here. I don't see how one can incorporate this field-based approach in the algebraic field theory approach, because in that approach, the smearing variables are presumably space-time coordinates, presumably, or could they possibly be operators? So they could be, I suppose, in the context of the fuzzy physics approach that many of you and Bal have pursued. And I think that'd be something I'd love to talk to you about. But of course, another thing here, and let me just make this final remark here. What about the fiber bundle approach? I simply don't see how many of those theories which have been undertaken by so many of you with so much success, I don't see whether it might be possible to incorporate these field-dependent space-time coordinates into that fiber bundle approach, because as I pointed out earlier, it appears that fiber bundle approach fails when one takes the full four-dimensional diffeomorphism covariance into account. Okay, so that's it. I want to just go through quickly so that people will have an opportunity, if they look at the film here, to see all these references. So I stopped.
Okay. Any questions? Questions? Yeah, I have a question myself. Is there some kind of dimensional reduction to, I don't know, to 1 + 1 dimensions or something like that, where you can work things out more explicitly?
That in principle is a possibility, but it's not something which I or my collaborators have attempted. I think it'd be worthwhile investigating though. So I think that would be an exciting exploration to undertake. So I confess here that I've only recently begun to try to look more carefully at the work which many of you have done. And I can see some potential areas in which it might be possible to incorporate some of these ideas within the formalisms that you folks have been undertaking.
Okay. Any other questions? Okay, let's thank Don again.
Thank you so much.
Thank you. So,
and I so wish I could have been there. Right? Okay.
Yeah. So next we have Kumar Gupta. Oh, good. So, Kumar will talk about black hole entropy and quantum information scrambling.
Okay, so I would like to start by thanking the organizers for inviting me and congratulating Bal on his birthday. So let's see. The topic is black hole entropy and quantum information scrambling, and this work was done with some people in Kolkata, Supriya Ghosh and Sashi Srivastava. So the plan of the talk is following. First, I'll give an introduction to a brief introduction to the subject. I don't think this audience needs any big introduction. Then I'll describe a model by Raphael, which was originally introduced by Raphael Sorkin, but a time-dependent version of that. Then we will talk about the solution of the time-dependent simple harmonic oscillator, which is relevant for that particular model. Then discuss entanglement dynamics and information scrambling via OTOC, and then we will make some concluding remarks. So one of the main motivations of this talk arises from black hole physics, in particular the description of black hole physics which was proposed by Raphael Sorkin. So a black hole horizon provides a bipartition of the space-time into an exterior and an interior. And with respect to the exterior region, the black hole behaves as a thermodynamic object. This is a well-known thing. And the Bekenstein-Hawking area law gives the entropy as proportional to the area of the horizon. Now what was, this was the standard law, and then Raphael Sorkin, as far as I know, he was the first person in 1986 who suggested that this thermodynamic entropy, or the entropy of the black hole being proportional to the horizon, could be interpreted as an entanglement entropy. So this was indeed an extraordinary suggestion, and which was repeated by Srednicki later in 1993, and these are the two seminal papers by Luca Bombelli, Ravinder Kaul, Juhan Lee, and Raphael Sorkin in 86, and then followed by Srednicki in 1993. But most of the stuff that Srednicki discussed was essentially in Raphael's paper. Okay. So Raphael calculated, although Raphael's paper talks about black holes, but in reality, this particular publication doesn't use much property of black hole at all. It gives, in fact, Raphael himself says this by evaluating this contribution in a simplified case. So the simplified case is what makes it tractable. And he and his collaborators essentially calculated the von Neumann entropy of a bunch of harmonic oscillators under bipartition. Okay? So it's a purely Gaussian model, and they made a bipartition and calculated the von Neumann entropy. And in the continuum limit, the whole of R3 was bipartition, and the boundary area was denoted by A, and what they found was that the entropy is proportional to the area divided by L square, where L is a ultraviolet cutoff. So as you can see immediately that if you remove the ultraviolet cutoff, the entropy diverges. And this kind of divergence of entanglement entropy, at least in the physics literature, to my knowledge, was first found by Raphael Sorkin. Nobody found this before him. Now what is the meaning of this divergence? This has become a topic of discussion in recent literature, thanks to several papers by Witten, who claims that this particular divergence that Raphael found has something to do with some deep structures of algebraic quantum field theory, which Bal has emphasized also many, many times. It has to do with certain properties of algebras observables for which I am not an expert, so I am not going to go into that details. Although I must say that there are other papers also recently which claim that this ultraviolet cutoff, the ultraviolet divergence is really independent of the issues that arise in algebraic quantum field theory. So there are other papers which say that there are two sources of the divergence of the entanglement entropy. One is coming from this ultraviolet divergence, the other is coming from some mathematical properties of algebras of observables in algebraic quantum field theory. Now, I cannot honestly figure out which is the right answer, but this is a discussion which goes on in the literature. Okay. So, in a slightly different vein, what we are also going to discuss this out of equilibrium quantum many-body system, which this Raphael-Sorkin's model would be in our context, and the non-equilibrium regime is achieved by quench in the system parameters, and that's what we are going to discuss. So this is a very interesting and important field of research today in many areas, not only in high energy, but also in condensed matter and various other subjects. And there are quite a few interesting experimental papers recently, in particular using cold atoms and optical lattices, where such things have actually been experimentally studied. For example, this is a paper, this Rajibul Islam is actually from Kolkata. He is now settled in Canada. He was the first author of this Nature paper, which experimentally detected this kind of entropies. And this is another paper from the Harvard group, another Harvard group, which also, well, it's not, Rajibul is not there, but by Marcus Greiner, which also made experimental studies of the quench in cold atom systems. And they actually produced graphs, which is really incredible. So anyway, so just to very briefly recap, so how do we understand entanglement entropy? This is not in quantum field theory. If I say quantum field theory, Bal will be the first person to object because this is only true in finite systems. So we have a state of a system described by a wave function. If it is a product states of two systems, then psi AB is psi A tensor psi B. If it is an entangled state, you cannot factorize the wave function in this fashion. And the density matrix is defined in the usual way, and you can define the reduced density matrix by tracing over either A or B, which gives the mixed state. And the von Neumann entropy is simply trace of rho A log rho A, which is given in terms of this expression, where Pi is at the eigenvalues of rho. This is absolutely standard textbook material. Again, I emphasize this is strictly true only for finite dimensional systems, not for relativistic quantum field theories. Okay. So the time dependent correlation functions in such systems can describe the propagation of quantum information. And one of the things which is being studied quite a bit recently is what is known as out of time ordered correlators, or OTOCs, which is defined in this particular fashion. It was first introduced in a completely different context by Russian physicists in 1969, but it has gained prominence in recent years due to many reasons, including that coming from high energy physics, string theory, as well as in condensed matter theory. Okay, this I already said. So now let us come to the system that we are going to study. So first we studied an extremely simple system, which is a Hamiltonian of a many-body system given by this particular expression. So these are just bunch of coupled harmonic oscillators. This is as simple as a system can be. And this is exactly what Raphael-Sorkin studied, except that he did not have time dependence in these parameters. So the new thing that we are doing is to making these parameters omega and k explicitly time dependence, and then study the behavior of the system under various kind of time dependencies. So now the question is, so suppose you take case n equal to 2, that is really the simplest thing, and then your Hamiltonian is just a two-body Hamiltonian, 2 coupled harmonic oscillators, which is related to the Bose-Hubbard model in certain contexts, but that's not so important for our purpose here. So, but this Hamiltonian, you can just go to the normal modes and then it completely decouples, right? You have two interacting harmonic oscillators, you go to normal modes and they completely decouple. So, once you have that, so what you want to do now is to solve a time dependent Schrodinger's equation given by this. This is our goal, to solve the time dependent Schrodinger's equation to begin with for this two body case. We will later go to the n body case. So, how would you do that? This thing has a very interesting history which I learned. So, in general, it's very, very difficult to solve such a time dependent problem where Hamiltonian is explicitly time dependent. If you want to analytically solve it exactly, it's very difficult. However, there are certain situations where you can find an invariant Hermitian operator which satisfies this equation. And if you can find such an invariant Hermitian operator, then knowing the eigenvalues of I, you can find the solutions of this equation. This was first discussed by Lewis and Riesenfeld in 1969, although I think there were previous papers by some Japanese groups indicating that. And okay, now how would you find an invariant operator? That is also not an easy task, but if H itself is an element of a dynamical algebra, then the task becomes simpler and this invariant operator can be written in terms of the elements of the dynamical algebra. So, for example, in the case of harmonic oscillator, the dynamical algebra is given by SU11. So, the Hamiltonian can be, the I can be written in terms of the elements of SU11 algebra and you can find a solution. So, I won't go very much into the detail of the derivation of the solution, but what was really at least eye-opener for me is that if you want to solve such a problem, let us say even for this extremely simple Hamiltonian, you can do so provided you can solve this particular equation. Okay? This is a complete miracle. So, look at this. This is a linear equation, linear Schrodinger's equation, where H is given by this expression, omega is time dependent. How will you find a solution to this? If you can solve this equation, which is called the Ermakov equation, which is a nonlinear differential equation, if you find this solution, then this psi here satisfies this. Now, how Ermakov discovered this equation, I really do not know. All his papers are written in Russian in the late 19th century. He was in Kiev in Ukraine doing this work. How he did it, I really couldn't figure it out. But this has become very, very popular these days among condensed matter physicists, some string theorists, high energy physicists, that whoever wants to study time dependent solutions to such problems, and this is not the only problem whose time dependent solution you can find with Ermakov, there are many others. Anyway, the bottom line is that we are going to, first we will solve such an equation and then we are going to derive the solution of the time dependent Schrodinger's equation. Okay. This is really some, okay, there are some very interesting mathematics behind it based on the representations of SU11, which is intimately related to that, but let us not go into that here. Sorry? No, B of t is what is going to be determined or found out by solving this equation. No, analytically. Numerically, I don't know how to do it. But for certain cases, you can do it analytically. That is the miraculous part. Well, for arbitrary omega t, you cannot do it. So the point is, for those omega t's, for which you can find a solution of this equation, for which you can find a solution of Ermakov equation, you have the solution of the time dependent Schrodinger's equation. This is the point. Okay? if you give absolutely arbitrary thing, whether you can solve this, I don't know. But there are huge maths literature on this equation as to how, this is a nonlinear differential equation, right? So finding solutions, I mean, there are no general techniques of finding solutions of nonlinear differential equations. But there is something called nonlinear superposition principle. And I don't want to get into the details of all that. There are well-developed techniques using which you can actually find solutions of this equation for certain kind of time-dependent omega. Okay, so we are going to restrict ourselves only to those cases. So very, very simple cases. Okay. So once you have a solution of the time-dependent Schrodinger's equation, you can write the wave function. These are just mathematical expressions, nothing fancy in this. So it's some exponentials like the Gaussians and with some time-dependent phases. So now the reduced density. So what happened to this? Okay. So the reduced density matrix can be calculated in the usual way. This is just straightforward calculation because you see there is nothing fancy going on. This is just Gaussian. So sorry. Yeah.
I guess my question is related with the
right.
Previous question, which is, and maybe you already showed it, but what form of omega t did you use?
I am coming to that. I didn't show that.
Shown it yet, no?
Right. I will show. So I am coming to that. Okay. Yeah. Sorry? See this, this equation is for that. Okay, I mean, if you can solve this equation, then this object satisfies this. We are doing for many degrees of freedom. Right, because see, what happens is, as I showed you, you decompose the system into normal modes. So once you decompose the system into normal modes, they are all independent, right? So you solve for each and then you go back.
So you do it for each normal mode separately?
Right.
Okay.
That's
Nice.
okay. That's kind of well, it's not cheating, but it's a technique. So, okay. Anything else on this? All right. So I want to emphasize that the whole thing becomes computationally very simple because you have reduced your system to just normal modes and Gaussians, and we all know how to handle Gaussians. So that's what makes it tractable. Although there are complicated time-dependent factors, but who cares about that? I mean, I'm just integrating on Gaussians. So okay. So the reduced density matrix you can calculate by integrating out 1 degree of freedom. And again, this looks complicated, but there is nothing profound in these things. And the reduced density matrix, you can find the eigenvalues from this integral equation. These are all standard given in Raphael's paper, Srednicki's paper, etc. All that goes through except that the eigenvalues are now time dependent and the von Neumann entropy has this form. So now let's come to the examples. Okay. So to answer Sachin's question, so let's say we start with this particular situation. We are making a, yeah. Commute with what? Yeah, sure. That's not, yeah. No, yeah, see, this is a global quench. This is not a ramping. This is a global quench. And that we checked. Yeah, that works. There is no problem with that. Okay. Even for ramping, it works in some cases. That decoupling part is not an issue. Okay. So first we use a global quench where omega initial is omega and omega final is 0, just to give some examples. So in this particular case, the solutions of Armakov equations are given by this. So there are two normal modes. So two different Bs, B1 and B2. B1 is this, B2 has an oscillatory behavior where M1, M2 are given in terms of the system parameters. So now if you calculate the von Neumann entropy, recall that von Neumann entropy was given by this particular formula. All you have to do is to plug your solution in, and your von Neumann entropy as a function of time behaves like this. Now these oscillations are coming because of the fact that you have explicitly time dependent cosine functions here. That is what is giving rise to these kind of oscillations. Okay? Just as an example. So you can do it for many other kind of oscillations. So for example, suppose you go from omega BH initial to omega BH final for various kind of values, you can still find solutions in terms of the two normal modes. And so just to give you another example, suppose omega BH initial is 3 and omega BH finals are given by different values, so you will find different behaviors. So they are all coming, in this particular case it's easy to understand why these oscillations are coming. Again, it has to do with this type of behavior of B1 and B2. Okay? So but our goal is not to solve the system for 2 degrees of freedom. We want to go to the thermodynamic limit and also use not this simple Cohen's protocol, but other Cohen's protocols to unravel what could possibly happen in quantum information scrambling. Okay. So again, these are various examples for simple systems in for 2 degrees of freedom, and you see a typical behavior like this. Okay. So now we really want to study the system for arbitrary n. Okay? Now you can do the whole calculation analytically for arbitrary n. There is no problem for that, because at the end of the day, you decompose into n normal modes, you solve for each one independently, and then you go back. So that's a pretty straightforward thing to do. So you can write it in some matrix form. The Hamiltonian has this, you can write it in this particular way. And then again, you can solve this equation, the time-dependent Schrodinger's equation, whose solution will be in terms of the Armakovs. But now there are typically n different solutions of n Armakov equations. It may happen that for certain cases, 1 or 2 solutions may match, but in general, you have n independent solutions of n Armakov equations, in terms of which you can find the solution of the time-dependent Schrodinger's equation for n coupled harmonic oscillators. Okay. And typically, the solutions of Armakov equations, these are the normal mode frequencies which have this particular form, and we choose initial conditions as the ground state of the time-dependent pre-quenched Hamiltonian of the n oscillator chain, which requires B01 and B dot 0 equal to 0. So basically, we are solving some time-dependent differential equation, and these are the boundary conditions for that. So now we don't simply want to solve with a simple quench. So what we did was to make a series of quenches. Now I want to emphasize that this series does not go to infinity for us. This is not a Floquet system we are solving. For Floquet, people have done many calculations. The physics is completely different for Floquet. This is not a Floquet system. This number of quenches are going to end at some point. It could be 3, it could be 5, and so on. Of course, we could carry this on to infinity analytically. That's not an issue, but that's not an issue as far as calculation is concerned, but for physics-wise, the answers could be different. Okay. So let's say we are quenching from omega initial equal to 3 to omega final equal to 20, and suppose these gaps are, let's say, 4 seconds. It could be anything. It could be 4 seconds, 400 seconds, 40 seconds, doesn't matter. I mean, you could solve the whole thing analytically. So I won't, you do this calculation. It's just generalization of the previous calculation, nothing more than that. And you can calculate the reduced density matrix. Reduced density matrix has this particular form. And note that the ratio, this is an important point, the ratio between the diagonal and a generic off-diagonal reduced density matrix can be written in this particular way. Now, why is this important? See, for a single quench, let's say for n equal to 20, so green line corresponds to n equal to 20, blue line corresponds to n equal to 500. These parameters, gamma minus beta and gamma, behave like this for a single quench, you see. But now notice what happens in a multiple quench. So suppose you have the same thing, n equal to 20 at n equal to 500. If you make multiple quenches, then gamma minus beta and gamma behave in a different way. You see, this gamma minus beta and gamma, particularly gamma, has picked up a much higher value. Here gamma was something like, in this particular example, maybe around 30. Here it has become close to 5,000. Now what, yeah.
When you have many oscillators, you have many normal modes,
Correct.
right? So I don't know if you already said this, but which frequency are you quenching?
All of them.
All of them,
Right.
every
Yeah,
and
yeah.
they are all not necessarily the same, but nevertheless you're quenching
That's right.
all of them
so,
by the.
see, each normal mode frequency would be determined in terms of the original system parameters.
That's right.
So I'm quenching on the original system parameters, and therefore I'm quenching on all normal mode frequencies. Okay. So now why am I emphasizing this point that gamma becomes large for multiple quench? Because if you go back here, you see as gamma becomes large, this ratio becomes very, very small. So essentially the how should I say, the reduced density matrix is becoming more and more diagonal. So the off-diagonal terms are getting dropped off as n becomes large and number of quenches are becoming large. So that is, I'm not claiming anything about thermalization, but that is typically what happens when you are approaching thermalization, that the off-diagonal terms starts to become smaller in the reduced density matrix and diagonal terms tend to dominate. Okay. So now for the entanglement entropy, again you see, although this is a completely integrable system, absolutely integrable, at least naively integrable system, the entanglement entropy saturates. It saturates pretty fast, which is also a little bit different compared to, if you compare here. Here the entanglement entropy did not saturate. It's keeping on oscillating. Whereas once you start to go to the thermodynamic limit and you look at various, if you increase n, let's say we considered 500, you could take even larger, and you start to increase the number of quenches, you see that these objects saturate, which is again an indication that this completely integrable system is sort of equilibrating, which is very, very counterintuitive. Such integrable systems do not normally equilibrate. I am not making any statement about thermalization because we have not done any analysis of thermalization, but it is beginning to equilibrate. That means things are becoming time independent, which is not expected in a usual integrable system. So the same thing happens for momentum distribution. The similar conclusions you can gain from that. Okay, so now let us come to the information scrambling. So the OTOC between two, I should have written local operators, M and N, separated by a lattice distance L, this is the standard definition. So if you expand this object, you will see that this is not time ordered. That's why there are some terms for which are time ordered, some terms are not. That is why it is called out of time ordered correlators. And we have chosen extremely simple operators, m as xi, mi as xi, and nj as pjc. So very, very simple thing. So for well separated local operators, which we have, the OTOC starts from a 0 value and then increases as the information propagates with the Lieb-Robinson velocity, right? This is the standard thing. And again, from our intuition in integrable systems, we would imagine that the information cannot get scrambled, should not get scrambled in an integrable system. So therefore, OTAC should be oscillating. It should not be saturating. That is what our intuition tells us. So you can again do this calculation analytically. It's a long calculation, but it's possible to do using the Armakow's. These expressions don't tell you much, but these figures might. So look at this situation where
Kumar, you have 10 minutes.
Yeah, I'll be done in 10 minutes. So look at this situation where n is 500 and we have considered 3 quenches, 3 situations. Green is just 1 quench, red is 3 quenches, this purple is 5 quenches, n equal to 500. And you see what is happening. So for 1 quench, OTOC will keep on oscillating like this, which is what you expect in an integrable model. For 3 quenches, it is still oscillating, but less. These dips are less than these green ones. And for 5 quenches, it's even lesser. So if you push this up to 9 quenches, 20 quenches, this guy is going to become more and more flat, which was really completely unexpected, at least to us. There is no intuition that tells you that in an integrable system, OTOC would behave like this. In other words, the information would be scrambling. You would expect that it will come back to 0 because it's not going to get scrambled. But that is exactly what is happening. Okay? Now look at this situation. So here, recall here that I fixed n equal to 500 and I considered these 3 quenches. The next one, I fixed the number of quenches to be 5, but I considered different number of degrees of freedom. And again the same thing happens. If n is 20, which is far away from the thermodynamic limit, OTOC starts to oscillate, dips. And as you increase n is 100, the dips are less, n is 500, it's more or less flat. So the bottom line is that if you remember, I emphasize this is a completely trivially integrable system. But still, even in this simple trivial case, if you go to the thermodynamic limit, n equal to 500 is thermodynamic limit for all practical purposes. And if you increase the number of quenches, the system seems to equilibrate. Okay? This is what we found to be utterly puzzling. But later we found that now this kind of behavior for integrable systems is being discussed by many people, and in particular, let's say by Alba and Calabrese and those people who have found that for systems which are integrable and yet solvable by Bethe ansatz, there is a particular kind of thermalization that can occur. This is called eigenstate thermalization. It's not full eigenstate thermalization, but a particular type of eigenstate thermalization can happen for such examples. And we found that for harmonic oscillator, very strangely, this was discussed in the 1940s by Bogolubov. He called something as transient chaos. And in particular, I think his student Cherkov and later Israelev, they all discussed this situation, which is called transient chaos, where this kind of behavior can happen. Bogolubov explicitly mentioned it. I don't know how he found it out, but he explicitly mentioned it. So it seems that the question of how or whether a system will thermalize and its relation to integrability is not as straightforward, at least in the quantum case, as one might think. In classical case, perhaps it's easier, but in quantum case, there are many subtleties. So I come to my summary. So I'm not going to read this out again. Essentially, the model that Sorkin proposed, which is a very, very simple model from which he could extract properties of black hole entropy. To the extent his conclusions are true, to that extent, our analysis also provides the behavior of at least this kind of quantum fields on that black hole background. So how the time dependence will, how the time dependence of entropy or the OTOC will should be observed in such backgrounds is described by this analysis. To the extent his analysis is applicable to the black hole entropy. And so I guess there are many other things one could do with this. Lot of people have now picked up these multiple quenches, and in circuit complexity, a lot of people are now studying these multiple quenches, and they are finding quite interesting answer in several IIT group. We know groups which are doing this. So that's it. Thanks.
Questions?
Yeah.
Oh,
So I don't know if it can be called like order to chaos transition or something like that. I don't know if it's like it can be called from order to chaos transition or something like that based on your parameter quenches. But my question is like, so is this generic for any parameter, or is there any specific value of quenches or specific frequency?
No, this is generic for.
This is
any
generic for
parameter.
all omegas.
Of course, as you see here, in the two particle case, it's easy to understand because the expressions are simple.
Right.
So you see there are different parameters that we are taking, and whether it is oscillating or this guy is also going to oscillate. It's just period is bigger.
Right.
Okay?
Right.
So
right.
this behavior is generic for any parameters. I mean any set of parameters. Okay, if you chase very pathological thing, there may be some corner of the parameter space where something funny might happen.
Right.
But generically, typically this is going to happen.
That's very surprising. I mean, like,
Yeah,
is it the quench that makes it quench rate that makes it the integrable to chaotic?
Okay, we didn't calculate the effect of the quench rate because we fixed it at that t equal to 4 seconds.
Right.
But what makes the difference is the thermodynamic limit and the number of quenches. The
I see.
quench rate part we did not check, but
Right.
it can be easily checked. Okay?
Nice. Okay, thanks.
And for the ramping also, it's possible to do. If you do the ramping, but you put in some, let's say, very arbitrary, very ad hoc quenches in between the ramping, then also this kind of thing can happen. This ramping part was being analyzed by Shumit Das and his collaborators.
Benjo?
Yeah, I may have missed what you meant by precisely by a quench, but how is the quench integrable?
The quench is integrable because of this Armakov. So it's exactly solvable. It's not just integrable. So you can so this omega is what is being quenched. Okay.
Yes.
So omega, let's say t less than 0 is 1, t greater than 0 is 2, for example. So that's the quench. That's a sudden global quench. That's
Yes.
what is called a sudden global quench. Now, why is it exactly solvable? Because for that time dependence of omega, you can solve the time dependent Schrödinger's equation.
Solvable and integrable aren't the same.
Okay, it's integrable. It's a harmonic oscillator, right? How I would like to know how it breaks integrability, but I couldn't find it.
Our integrability has conserved quantities.
It does.
So are the quantities conserved through the quench?
So right before the quench and after the quench, it's just harmonic oscillator. It's a sudden global quench, right?
So presumably they are not the same.
But they are there.
The constants of motion shouldn't be there.
They're different, but they are there.
Then it's not integrable.
Okay, fine. But people call this integrable also. I don't know. I honestly don't know the terminology, but this is typically what, in fact, I don't know the details, but typically this is considered as a paradigm of integrability.
I guess the point is that something can be solvable and not be integrable. I think that.
Perhaps it can be. But at least for this kind of system, even if it is not integrable, you see, the point is that when you have small number of particles and just a single quench, it shows in terms of equilibration, it shows all the behavior of an integrable system. But when you go to the other case, here, when your number increases to the thermodynamic limit and the number of quench increases, it shows the behavior of an equilibrating system. So this is for sure, this is just calculation. Whether you call it integrable or anything else is terminology. But this difference of behavior is there.
Other questions? Oh, Bal has a question.
Yes,
This is not exactly what you're doing here,
right.
but I think it is somehow related. In QCD, let us say, the generic quantum state in the colored state, okay, is necessarily entangled. Okay?
Yes.
This can be proved, okay, and we have proved it. Okay, now it happens that the Hamiltonian of the system, there is some non-abelian chemical potential I talked about earlier, and it changes this entanglement as a function of time, and consequently also if you compute entropy, this entanglement is, I would say it's a classical entanglement, okay? And as you change as you look at the time evolution, for certain particular chemical potentials, it oscillates like this.
Oh,
Exactly.
I see.
Yeah. But for some other orbits, okay, this entanglement is ergodic. Okay?
I see.
It goes ergodically through all possible entanglements that you can imagine. Okay?
Okay.
I think that this is related to the phenomenon you are finding in finite dimensions.
That very well could be. That's an extremely interesting thing that you said. I didn't know that it can oscillate in such cases. But here, you see, here the system being analytically so trivial, it's kind of easy to understand where the oscillations are coming from. They are simply coming from the n normal mode, Armakovs for the n normal modes, which have this oscillatory behavior.
One small thing. With respect to solvability and integrability, actually in the harmonic oscillator problem at least, it was shown by Padmanabhan or Paddy, that there is this Yermakov-Lewis invariant which commutes with the Hamiltonian.
Right,
So that there is some conserved quantity
right.
which is kind of thing which is needed for integrability. That is what is the issue.
See, that is what I said at the very beginning here. So you are absolutely right. I mean, the way you solve, how are you going to solve this guy? It's not an easy thing to solve. So you have to first find an invariant, this I, and which di dt is 0. Okay? So if you can find the invariant in terms of the eigenvalues of that, you can find the solutions of the harmonic, the Hamiltonian. And that is where okay, this is general, this is completely general, and for harmonic oscillator or let's say Hamiltonian, for which AC11 is the spectrum generating algebra, for that the Armakov comes. So there are a whole lot of models. You can do Calogero models, you can do harmonic oscillator, you can do many things for which this Armakov guy shows up. Thank you.
So we'll reconvene in 10 minutes.
This one.
Okay, so welcome to the second session of the morning. So we have Bala Satyabalan from IMSC speaking about aspects of the map from exact renormalization group to the holographic renormalization group. Bala?
Yeah.
Please
It's not here.
settle down. Yeah, I guess we should. Yeah, we'll wait for.
Yeah. Anyway, I'll thank the organizers for inviting me to give a talk, and congratulations to Bal and best wishes. So I'm going to talk about some aspects of the map from exact RG to holographic RG. So, I'm not actually what I'm going to do is to give a summary of some of the things that we've done and focus on trying to clarify some aspects, one particular aspect of that. And I just realized listening to the previous speaker, Kumar Gupta, that there's some connection between the mathematics of this map and some of the problems that he was mentioning, which I was not aware of, but I realize now. So, let's move this. This is not moving. No, I want to change it. I can press the space bar now. Okay. I'll use this. Okay, so here's the outline of the talk. So, pointer. No, anyway. So I'll talk about, the introduction will be describing, the first two parts will be describing what we've done. And I'm going to emphasize the third part and then say a few things. And then I'll try to say something about the DS-CFT if I can. Very preliminary remarks. So let me begin with the introduction. So what we, as you all know about ADS-CFT, there is a connection between, a duality between a boundary CFT and a bulk gravity theory. And there is something called holographic. So maybe I should just read it, it'll be more systematic. So ADS-CFT conjecture says that the dual to a CFT in D dimensions is a gravity theory in ADS D+1. And a famous example of that is n equals 4 Yang-Mills in 4 dimensions, dual to 2B string theory in ADS5. So it arose in string theory, and in string theory, this duality is not very, it's not very unexpected because there is a duality between open strings and closed strings, where open string trees are similar to open string loops are similar to closed string trees, and closed strings contain gravity, and open strings are basically Yang-Mills. So as far as I'm concerned, I'm not interested in all aspects of the duality, but the point that I'm interested in is this point that the radial coordinate of the ADS space in this choice, this choice of coordinate is very easy, behaves like a scale for the boundary theory. So here xi are the boundary coordinates, d-dimensional boundary coordinates. Z is the radial coordinate. And you can see that the dxi is divided by z squared. So when z changes, you're changing the scale of the boundary distance element. So it acts like a scale. So if you accept the ADS-CFT conjecture that these two theories are the dual descriptions of each other, then changing z will correspond to a scale transformation of the boundary theory, which is therefore a renormalization group evolution. So the evolution in the radial evolution in the bulk, which is just it's just that, but because of this boundary connection, it's referred to as holographic RG. Okay, otherwise, it's just a radial evolution. From the boundary point of view, it looks like an RG. This is assuming so you have to accept this conjecture for this to be true. And what are the things we wanted to, well, one of the things we did, there's a paper with, I should mention the date, this was in 2017 with Hidenori. We showed that starting from an exact RG equations of a CFT, one can derive the holographic RG equations by an explicit mathematical mapping. So if you don't assume this conjecture, and you can ask whether you can start with the RG equations of a boundary theory, can you show that it looks like the radial evolution of a field theory in a DS space? And so we were able to do that in a simple example where the fields were fundamental fields. And later, in a paper with Pavan Dharani Pragada, who's a student here, and Semanti Datta, who's now a postdoc at ISC, we showed that these techniques apply to conserved vector currents, and it gives a dynamical Maxwell field, and applied to the energy momentum tensor of the boundary theory, it gives dynamical gravity. Okay, so at the linearized level. So this was done at the linearized level, namely the leading equations of motion. For a simpler case of a scalar, the ON model, this is, I didn't say it here, but this is applied to the ON model where you have n scalars, free scalars in the boundary theory. But you can study the ON model at a Wilson-Fisher fixed point, and you can study composites of that and do the same map, and you can get out an interacting bulk theory with where you get a kinetic term plus some cubic terms, and that also agrees with what is known from the conventional ADS safety. So indeed, this seems to be a valid method of deriving the holographic RG equations. So I just mentioned, repeat some. So it's interesting because it comes out of RG and does not require the ADS-CFT conjecture in any form, this map. In particular, it does not invoke string theory and seems more general. Because the usual examples of ADS-CFT seem to have come out of string theory where it is to be expected, but here it doesn't seem to be required. Of course, since you have a gravity, quantum gravity in the bulk, you might say it's only well-defined if you have string theory. So in that sense, string theory does enter. But at least superficially, there doesn't seem to be any requirement of string theory. So this construction of the holographic RG seems to give some insight into why ADS-CFT correspondence exists. And it gives another interesting way to understand gravity. It seems to come out of RG of some field theory which doesn't have RG. I mean, it doesn't have gravity. Okay, so now what I'm going to do is I'm going to summarize the map. So, and then we'll focus on one aspect of it. So the 3 steps. So I should mention that the work that I'm going to talk about is also done in collaboration with the same 2 people, Pavan and Semanti. So this is the map we did with Sonoda. So we wrote down Polchinski's ERG equation for a d-dimensional field theory. That's the first step. The second step is to write down an evolution operator for this equation. And that turns out to be simple because the equation has a simple form. So you can write the evolution operator as a d+1 dimensional field theory, functional integral of that. And the extra dimension in that d+1 is, of course, the scale, z, which I've written as e to the power of t. So, of course, already you have a functional integral in d+1 dimensions. So in that sense, it's already holographic, but it has nothing to do with ADS. Now, this third step, you map this field theory in d+1 dimension to a standard field theory in Euclidean. This is all in Euclidean space because we're talking about a boundary theory which is Euclidean. You can map this to a field theory in ADS d+1. Okay. So these are the 3 steps, and I'll just go over them a little more detail, and then we'll concentrate. I'm going to concentrate on step 3 for the rest of the talk. So I'm going to say ADS d+1 emerges in the 3rd step, and this step is the main focus of this talk. So I'm not going to say anything new. I'm just going to consider other maps to clarify it, and at that point, I find some of the comments made by Kumar in the previous talk are relevant. Very similar things happen here. So one can ask, are there other possibilities? For instance, in fact, when I first gave this talk at IMSC, I remember the first question someone asked was, can you do this for other spaces? Why ADS? Why not DS? And it seems that you can. So you can make some connection with DS CFT also. So studying other possibilities also helps us understand better what is going on. Okay, so that's the aim of the talk. So as I said, it's just going to clarify one aspect of this map. There's nothing new. Okay, so the first step is, this is Polchinski's equation. So I just have to define a few terms. So G, I think I've written it here. G is this pointer does, here, that does work. So G is a cutoff propagator. Okay, so it propagates only, well, it's an analytic form, but it basically propagates modes lower than lambda. And psi is just e to the power of, I've written it in this suggestive form, but psi is just e to the power of minus si. I stands for interacting. So this is the interacting part of the Wilson action. So the Wilson action is this. You take out the kinetic term, and what is left is the interacting part. And this equation tells you how the interaction, this Wilson action flows in T, which is this RG scale. So as you increase T, lambda is decreasing, so you're flowing towards the infrared. So T is a flow towards infrared. So this is Polchinski's equation. It's very easy to derive, but I'm not going to do it. And actually, for the purpose of this talk, we'll take D equals 0. So it's just a quantum mechanical system. And instead of calling it phi of P is the momentum, I'll just call it X. So it looks like a simple Schrodinger equation. So you're just studying quantum mechanics now. And whatever you say, whatever is done here, it can easily generalize to D evolution. So it's not a problem. And so, of course, for this system, P, remember, was the momentum in the flat directions, the boundary momenta. And here it has no meaning, but it's just written as a parameter. So when you generalize to D dimensions, all these x's will be replaced by phi of P. I think this ladder is not working. Okay. Okay, so here's the solution. So you know, of course, I should mention, how do we go back? Is it possible to go back? This is just Schrodinger's equation without the I. So it's a diffusion equation. So you can use the Feynman path integral as a solution. And here it is. So psi of xi ti is basically your initial Wilson action, parameterized by the xi. This is the evolution operator. So it's so the initial thing is a zero-dimensional. So I've put the boundary conditions. X at ti is xi, x at t is x, and then you get the wave function at t. But this is not a wave function. It's a probability. It's like e to the power of minus s I x. So here boundary is a zero-dimensional field theory. The bulk is a one-dimensional field theory with a funny kinetic term, funny because of that g dot p term. And this is holography in its simplest form. But now we're going to change variables to bring the kinetic term to a recognizable form. So this is what we did in our 2017 paper. I'll just repeat what we did. So this is a map. You replace, it's just a simple change of variables here, or a field redefinition. You replace x by f times y, change of variables, and choose your f so that the g dot disappears. So f squared is taken as minus g dot. I've just called it, for the purpose of this talk, I'll just call it an f map. So if I refer to this map, this is what I mean. And if you do that, you get this, what I've written here, where the second term is obtained after the substitution and some and throwing away some boundary terms. You get a term like this. Note this form because this is going to be used again. So it's just the form e to the power of, I've written it in this form, but of course e to the power of log f is just f. It's e to the power of log f, d squared by dt squared, e to the power of minus log f. In higher dimensions, it will be the same thing except with some powers of z in between. Now the whole point is, p is a parameter in this theory. I'm going to choose this to be this, where p is some parameter, m is some parameter, r is some parameter. Okay? And lo and behold, you get a scalar field theory in ADS space. Okay? So this is ADS 0 plus 1. And so here, if you take ADS d plus 1, you will get the corresponding thing in d dimensions. So what does this do? This now my variables are y, so I get a evolution of e to the power of minus si in terms of y and t, and the functional integral is an integral over an ADS space. Okay? So this is precisely what holographic RG says, so, as was defined in the original ADS CFT correspondence. The bulk theory is an ADS theory, and integrating that is supposed to evolve the boundaries, the field, the boundary action sitting at some point on at Ti, and as you evolve that T, that's radial evolution, that's supposed to give you RG of the boundary. So here we've started from the RG end and got the radial evolution. And if you generalize, as I said, if you generalize this to d dimensions, you get field theory in ADS d plus 1. Okay? Now there's some, what is it, before I go on? So before I do that, so this is, as I said, this is for simple, the field on the boundary and the field in the bulk are the same elementary fields. There's some generalization you have to do, which I haven't integrated shown here, when you deal with composite operators. Okay, so when you deal with gravity and Yang-Mills, etc., the boundary or the ON model, the boundary fields are not what are going to occur in the bulk. The composites of the boundary fields will be used, and you can introduce a source for the composite, or you can introduce auxiliary fields for the composite. And what occurs in the bulk will be those auxiliary fields. And to do that, you have to write the corresponding Polchinski equation for the composite field action. So that's a somewhat non-trivial step, but I'm not talking about that here. So here we'll just stick with a simple example and proceed with this, where you just, the fields in the boundary are the same as the fields in the bulk, just to illustrate the point. Yeah. Yes. No, it's just a change of variables. P is a parameter. Think of it as a parameter. So the new variable is defined in terms of the old variable. So there's some underlying, there's a P. Yeah. Family of mappings, yes. X is, see, these are all integration variables. You're going to integrate over X. It's a function, it's a... No, I'm taking, y is a function of t, x is a function of t. The action will have a p in it. The action, the p enters in the action. Because at the end of the day, x is just a variable of integration. You're going to integrate over all x's. Okay, so we would like to understand this map. So I consider the quantum mechanical problem of a free particle with a time-dependent map. So this is where some of the things that Kumar was talking about enter. And so the ERG equation, if you analytically continue it, oh, sorry, what did I do? So this, if you take m as minus 1 over g dot, that's the ERG equation. If you analytically continue this to real time, then you just get the Schrodinger equation and the usual path integral with a particle of mass m. And now this mass is a function of t, time. Okay, so now the crucial point is conceptually psi now is an actual wave function. It's not in the Euclidean version, it was a probability. Here it's a wave function. So the interpretation is different, but the two are just just an analytical continuation of each other. So we'll do the same thing that I did for that problem. And I'll put x equals fy with f squared taken as 1 over m. And of course, you get back the same. Oh, what did I do? Yeah, can you see the red? Yeah. So you get the same combination. And now I'm just going to explore, choose this, instead of choosing it to be z squared, p squared, plus m squared, r squared, etc. Just take the simplest example for harmonic oscillator. Okay, take omega squared, and you get a harmonic oscillator. Okay. Here, there is no time dependence in this. That's all gone. And of course, m is constrained because f solves this equation. So your m, well, 1 over f has to be of this form, so your m has to be the square of that, cos squared, something like that. Okay? But the point is you get a harmonic oscillator, and this is interesting. And yeah, so this is where the thing that's mentioned by Kumar come out. I found out that I did a search and I found that Padmanabhan has he's looked at this problem. This is 2018 actually, not 17. I don't know in what context. He's done the same thing that we did, but his motivation is completely different. He does the same map, and he shows, and he says that the energy of the oscillator is an invariant, and expressed in terms of the original variable, it's this quantity, which is unintuitive object, but it's just the energy of the oscillator. And he points out that these are just the Ermakov-Lewis invariants that Kumar and all were mentioning. So this method gives a nice way of deriving this, which is different from the method that Kumar gave. I think he mentioned some Russian papers. So I'm not going to use this much. I just want to point out that the same thing is happening in the ADS case also. So it's just a different map. Of course, now you can explore and try other maps. But now you can do the analytical continuation of this with the free particle Schrodinger equation and do the same thing. And actually, you can try to do this at the level of the equation. So previously, I was doing it for an action and the path integral. Now you can do it at the level of the equation. And the way to think about it is these are, you should think of these as canonical transformations. Anything that preserves the commutator is defined as a canonical transformation. So you can show that if you do this, if you define your wave function, a new wave function like this, with some alpha which is defined to be that, then this equation, and you choose the same f that I did before, the action, you will get the Schrodinger equation for harmonic oscillator. And there's a constant due to some ordering issues that comes out, but this constant doesn't depend on y. It just scales the wave function by a fixed amount, so it doesn't really have much importance. So you get the same equation, the same method. So that's another way to understand this map. What you're doing is some kind of a quantum mechanical canonical transformation. This is also interesting. There are some papers by people studying in the context of ADS safety, trying to map the RG equation to the bulk, and they find that their kinetic term has non-local terms, and they use canonical transformations to get rid of the non-locality. So this seems to be doing that, getting rid of all the non-locality immediately, because the G of P is in some sense infinite number of derivatives, so it's a non-local thing. So this is getting rid of that. So that's another way to think of it. Okay, so analytical continuation. So now if you analytically continue the Schrodinger equation, you get the ERG equation. The ERG means exact RG equation. And so you can do the same thing for the harmonic oscillator. Choose this, and you'll get the Euclidean harmonic oscillator. So you can start with the Schrodinger equation and do this map, and you'll get a Euclidean, you'll get a equation for the wave function. If you do for the Euclidean case, then you get an equation for the Euclidean version of the wave function, which is a probability, which is e to the power of minus s. And these kind of conditions remain the same. So now you can, okay, so here's a summary. The Euclidean free particle ERG equation can be mapped to a Euclidean harmonic oscillator if you choose this, and the Euclidean ADS theory if you choose the second one. So this is, of course, I've done all this in 0 dimensions, but you can do this in d dimensions, as mentioned. Now you can analytically continue the ERG equation to get a free particle Schrodinger equation, but you could equally well analytically continue, wait, I haven't done that. The quantum mechanical free particle Schrodinger equation can be mapped to a harmonic oscillator if we choose this. So now the question is, can you, instead of omega squared, if I choose z squared, p squared plus z squared, r squared, is there an analytical continuation of that? And the answer is yes. Answer is, again, that's a well-known thing. You get ds. The analytical continuation you do is I eta, you call z as I eta, r as I L. Choose the same map that we did before, this map, and you get the quantum mechanical evolution for a wave function in de Sitter. But I emphasize that now we're doing quantum mechanics, it's not statistical mechanics, so psi is an actual wave function. Previously, psi was just e to the power of minus s. Here it's an actual wave function. So that's basically, now I'm just going to summarize the conclusion and that's the end of the talk. So this map can be understood as canonical transformations in the quantum mechanical problem. So you can map the free particle with prescribed time-dependent mass to a harmonic oscillator. In the Euclidean case, psi refers to a probability of the form e to the power of minus s. In the Lorentzian case, it is a quantum mechanical wave function. The ERG equation maps to a holographic RG equation for psi. You could equally well analytically continue the Schrodinger equation, and it maps to a quantum mechanical evolution equation for psi, which is of that form. And this can be generalized to d dimensions. So there are two things you're doing. There's a map and there's an analytical continuation. And you can do the map first and then analytically continue, or you can first do the analytical continuation and then do the map. And either way, you'll get the same thing. So you could start with the ERG equation and analytically continue to a free particle Schrodinger equation, which maps to quantum mechanical evolution in de Sitter space. Okay? Or you can start with the ERG equation, map it to holographic RG, which is this map of change of variables, and then analytically continue to, and then you get Euclidean ADS, which can be analytically continued to quantum mechanical evolution in de Sitter spacetime. So at the end of the day, this gives us the statement of the DS-CFT conjecture, which has been made before. And the statement is this is a last slide. Psi, the wave function of de Sitter, is related to, so the left-hand side is a wave function. So the left-hand side refers to a d-dimensional spatial slice of a d plus 1 dimensional quantum mechanical theory. And you're getting a wave function on that. The right-hand side is actually something like e to the power of minus the Wilson action, which is like a partition function, but analytically continued. So this is a partition function or a generating function of a CFT, and you analytically continue it. So this is the way, and so in this sense, to the extent that RG can be mapped to holographic RG in Euclidean ADS, you can map RG to de Sitter wave function also exactly the same way, with an intermediate step of analytical continuation. So that's basically what I had to say. So I've left out all the complications of dealing with composite operators, etc. But at the simplest level, this is all there is to it. Of course, now you can go ahead and start talking about what you're going to do with this wave function, how you calculate expectation values, etc. This is done in some papers, and they point out that calculating expectation values with this object in a quantum mechanical theory gives different results from the analytical continuation of this, because when you calculate an expectation value of the wave function, you have to take psi star psi. So you don't just use psi because it's a wave function, not a probability. Okay, but those are all, there's nothing new in all that. So I think I'll stop here and
Any questions on this? Yeah. I think you should go first. Yeah.
In all the slides, it looks like there is some non-locality and like by some change of variable,
yeah.
you get locality. So I'm confused, like locality is supposed to be some like physical property, right? Like how can by change of variable you can?
No, it's not. The point is it's not a different. It's not really a non-local theory. The non-localities of the form when you cut off a field theory, the non-locality emerges because you're integrating out modes, and so it's not an unphysical non-locality. It's a physical. Your bare theory is local even in the CFT. It's because you integrated out some modes that it looks non-local. But we're saying we can map that to a problem which remains local all along. That's all. So your starting theory is local, it remains local. But the price you pay is that the action depends on the coordinate z, but it depends in such a nice way that it looks like an ADS space.
And I mean, in this whole analysis, this particular property of the metric is very important. Like this.
The ADS metric.
Huh.
Yes, the ADS metric has this nice form that the z tracks the scaling. The z dependence tracks the scaling, which is what you want in an RG also. In a dimension, when you write in terms of dimensionless parameters, say near a fixed point, you don't have dimensionless parameters, so all dimensions are made up with powers of lambda. And that becomes 1 over z, and so all those powers of lambda become powers of z, and that's exactly what is required in an ADS metric.
So if I have started with some other metric in the ADS, it will not be that much visible. Right.
Oh, you mean other choice of metric? Yeah, it would be not so. It would not be so obvious as in this metric, but I think the results will be the same. Yeah.
Okay, thank you.
Let me say, this is my ignorance.
Okay.
It seems to me that ADS is ruled out experimentally. Okay? That's what I hear.
ADS?
So why, and it is also for cosmic scales, and this is, I suppose, for microscopic physics. So I don't understand the relevance of this correspondence at all. Okay? If it is for microscopic physics, where does ADS come from? A convenience. And you said DS.
Yeah.
DS says the orbits are accelerating particles in the Rindler wedge.
Yes, yes.
And the operator which does the evolution is the boost operator. But the boost operator is unbounded below. So the energy is unbounded below. Again, I don't understand the physics. I mean, you can do mathematical calculation. But what is the physics of this, I don't understand. Also, cosmic scales, there are all kinds of things.
No, you have a wave function evolving it quantum mechanically, that's all.
So the energy, the expectation value of the energy will be unbounded below. So I don't understand.
But we are living in a de Sitter space.
Huh?
We live in a de Sitter space.
De Sitter space, it will be unbounded below, yes.
Well, whatever it is, that's the real world, huh?
Unbounded below.
We are in a de Sitter space. There is a cosmological
That is
concept.
in large. I don't know that that de Sitter space is relevant for microscopic physics.
Oh, okay. No.
That I don't know, okay? Because there are so many things happening.
No, actually, yeah, so I'm not addressing any of those questions. All I'm doing is making the connection between the DSCFT correspondence that people have made in the literature, the ADS-CFT correspondence that people have made in the literature, and how it all ties up together in a mathematical form.
But what is its physical relevance?
Of ADS-CFT?
This whole approach.
It's
very
physical
popular.
relevance is just that you have a field CFT, and it has a dual description which allows you, which is a useful description. That's all. But it's also a way of understanding. It's also a way of understanding how dynamical gravity can come. Imagine the ADS scale is very large, so it's very close to flat space. So you have a dynamical gravity coming out of as dual to a theory that is no. Yeah, okay. I mean, I have nothing more to say than what anyone else has to say.
So Mana, when you went to the DSCFT,
Yes,
like, so which do you get CFT at scry plus or scry minus, or it doesn't, it depends
So
on how
here,
you get
we're using those coordinates where at t equals minus infinity, it's a light-like thing, and t equals plus infinity is space-like.
So you get Poincare patch.
Yeah.
So
yeah,
when you
it's
do
a
the
Poincare
full,
patch. Yeah, it's a Poincare patch. Yes.
So when you full RG evolution, you go from the one of the boundary to the horizon.
Yes, correct, correct. Or from the horizon to the boundary, whichever way you want to do it. Yeah.
So, Paul, let me just add a few words about the physical relevance of the ADS CFT correspondence. So DS CFT, I think, is very interesting. I'm not sure I know how to answer the question, but it's interesting since we live in de Sitter space, but I put that aside. So you can try to use ADS CFT in two ways. One is to learn about quantum gravity, which maybe others can speak more about, or it's to learn about the gauge theory side. And so in terms of thinking about how does it relate to the real world, you can either try to relate it to the quantum gravity of the real world, which is what many people have done, or you can think of the CFT as a model for QCD. In particular, if you go to finite temperature, n equals 4 Super-Yang-Mills at strong coupling and finite temperature is a nice toy model for quark gluon plasma at high temperatures. And the big advantage of ADS-CFT is that strong coupling in the gauge theory gives you classical general relativity on the ADS side. So impossible questions like equilibration, strong coupling dynamics, viscosity, transport coefficients, things that are very, very hard to calculate in quantum field theory become easy calculations in gravity. So anyway, just to say that there are ways of relating what Satyapalan has talked about to the real world, either by trying to think of the real world as the gravity side or by trying to think of the real world as the gauge theory side.
We can move on to Justin.
Thank you.
We have Justin David talking about entanglement properties of the graviton.
Yeah, so thank the organizers for inviting me, yeah, maybe my talk is a little outside this community, but maybe because I'm not going to stay till the end, maybe I can just tell congratulations to Bal. And in fact, just some reminiscence. I met Bal, I think, first time when I was a student at Tata Institute, and he was talking about posets, I think, at that time. And the next time is sort of the time I met him at IOP. There was some meeting at IOP that time. All the communities were together, the string theory and the general field theory community. And that time, I think he spent some time with me in one of the rooms. And at that time, I was learning string perturbation theory, and he was listening to what I was learning, and he was giving me comments. And now when I go back and think about it, and he's a senior professor, I was just a second-year student or something, I can't imagine myself listening like that to somebody. And I thank for all that interactions, and we had times later on together interacting, and so I thank you, Bal, and congratulations. So let me talk about entanglement properties of graviton, and this was work done with the student Jyoti Moy at ISC. And let me begin with a brief introduction. So entanglement is actually a difficult quantity to evaluate in quantum field theory, and evaluating it for gauge theories with gauge symmetry, it's even more difficult, even if they are free. And the usual method has been the replica trick, which has been most successful in 2D CFTs. And as many of us here know, that entanglement entropy has played a crucial role in understanding holography as well as black hole physics. Now, in spite of that, in spite of the fact entanglement has played a crucial role in gravity, there's been very little study of entanglement entropy of just gravitons. And in fact, one would need that for understanding formulas like these, which are sort of, I think this, like this, which occur, recently. It has been, these such generalized entropy formulas have played a role in black hole information paradox, in which this quantity S bulk involves, partitioning the region into two regions in which one includes entanglement entropy of gravitons also. So, these are sufficient motivations to study entanglement properties of the gravitons. And in fact, graviton is a fundamental particle in nature, and it is sort of just a natural thing to understand what it is, what its entanglement properties are. Now, what I will focus on is a restricted case, just linearized graviton, the linearized theory, and which admits a particular gauge symmetry. The simple question one can ask is that, what's the logarithmic, as in the previous talks, people have talked about the area of term in entropy, but in entanglement entropy. But when you partition a region into two parts, there are, especially in even dimensions, there is a logarithmic growth term. And and in fact, that is the sort of renormalization group invariant term. And what is the logarithmic coefficient of entanglement entropy of a spherical surface? You just partition it into a sphere and ask the question, what is the logarithmic coefficient of that entanglement entropy? So, for instance, for free scalars, this is the numbers, -1 by 90, 11 by 90, and Cassini and Huerta have evaluated it. And can one study these, for the graviton? Suppose there are excited, this is for the vacuum, suppose there are excited states, can one study entanglement of excited states involving graviton? So these are the very simple questions one is asking. Now, for theories with gauge symmetry, due to the Gauss law, the Hilbert space does not factorize into two subregions. I will detail it a little bit later again. And it actually factorizes as sum of superselection sectors. And there is a contribution of entanglement due to the sum. Now, for a theory with gravitons, how do you find the superselection sectors? How do you find the entanglement entropy of these sectors? Now, and the second question is, okay, you have the ground state, can you study excited states over it? So let's just begin with the definitions again, just simple. So we begin with a spatial region, a spatial subregion in CFT, and we consider it at a time slice, divided into two regions, A and A bar. A is a sphere for us in all the cases, actually, except the last if I have time. And suppose the Hilbert space factorizes into two subparts. Then one reduces, evaluates the reduced density matrix by tracing over the complement region and takes the von Neumann entropy of that particular reduced density matrix. And that's your definition. And if you're dealing with spin systems, or a lattice system in which degrees of freedom are spins, then the Hilbert space does factorize. And theories, and this trace can be carried out, and in principle, you can evaluate the entanglement. So theories with gauge symmetry, including gravity, does not admit this simple factorization. The gauge invariant factor Hilbert space doesn't factorize, and let's see this for the Maxwell's theory. Yeah. Scalars? It does not. Like, suppose it's just spin system. Okay. Yes. Yes. Yeah. Yeah. So there is an ambiguity in definition of that local algebra. Yes, indeed. Yes. Yeah.
No.
For even scalars. Yeah, I understand that.
No,
yeah.
whatever it is universal. Type 3.1 is the characteristic property of all local quantum field theories, apparently also related to gauge theories. And there is a general theorem that you cannot factorize, you cannot localize these algebras in terms of states.
Yes.
So the, Bond rule does not apply.
Yeah. Yeah, okay, I understand for the scalars, but so when you have, that leads to an ambiguity on defining sort of the edge modes.
No,
yeah.
No, that's not correct. So
that's not clear.
There is a old result due to Fermi, that if you assume factorization, it leads to causality violations. Okay, and it was resolved only let's say 10, 12 years ago. because of the assumption of factorization of bound rule. For this is something to do with electromagnetism.
This is for electromagnetism.
The problem you are dealing with is that there is a split property.
Split property, yeah.
For space-time localized algebras, and the split algebra, the splitting thing is type 1. So that does admit density matrices, which can be restricted to type 1 has trace class operators. You can so then you get a mixed state a priori. And I saw a paper today from Kumar Gupta that Roberto Longo and a colleague of his have proved, I don't know how they did it, that even in this case, they can find a finite entropy. This I don't know how they did.
So here, of course, I mean, when you talk about gauge symmetries, I mean, because of the Gauss law, there is no fact. That's the simplest thing I'm talking about.
Yeah,
the Gauss law. Yeah.
But the theorems that they are quoting seems to be completely general. It seems to have very little to do with the kind of quantum field theory you're dealing with locally.
Right.
Gauss
but
law
then, okay, so, so, okay, let me just go ahead, and then we will come back, and let's see what, So, let's go ahead with this Gauss law, I mean, for the Maxwell's theory, and what I mean, I'm meaning factorizability in a very restricted sense only. So, due to the fact that the Gauss law must satisfy, states must satisfy the Gauss law, the Hilbert space actually breaks down into this form. So there is this sum over the electric sectors. I will sort of detail this later, and the Hilbert space, inside and outside Hilbert spaces run over the sectors actually. So so the Gauss law actually requires the radial electric field to be identical inside and outside. So let me just go to the explicitly. Here is some picture. And this is the radial electric field, and the electric field configurations should be matched inside and outside. And just to see that explicitly, we choose a gauge. So we are like in Maxwell's theory, we choose a gauge, and the states satisfy this property, the Gauss law property. And this, of course, by everybody's argument, the pillbox argument leads to the fact that inside and outside electric field should be matched. And gauge invariant operators, suppose you built Hilbert spaces inside, the gauge invariant operator created by Wilson loops, little Wilson loops, cannot change this electric field configurations. So, and the Gauss law links the inside and outside. So therefore, just choosing a region, the Hilbert spaces actually, the Hilbert space breaks down into this particular form. It tensor products, but sum over the electric field configurations. So then how do you define the entanglement for such a particular breakup? So consider a density matrix of this form, right? And there is a subscript here, which of a particular sector we are looking, so particular superselection sector labeled by the electric field configuration. And in particular, the Hilbert space, in this particular configuration, we can take the reduced density matrix. So given a particular electric field configuration, we take the reduced density matrix. And the full density matrix is the sum over the superselection sectors, sum over the PE, where probability of a given electric field configuration. Then we form the reduced density matrix over the sum. So we just carry out this thing. We form the reduced density matrix over the sum here, so where the PE is there. And evaluating the von Neumann formula, we have this particular term. We have this particular expression in which this contribution is the contribution which I call as the contribution from the edge modes. This is basically the probability or the entanglement due to the superselection sectors, due to the fact that there are superselection sectors. So it is this particular contribution which I call the contribution of the edge modes. Maybe there are various things in the literature, but this is what I am calling as the contribution of the edge modes. Now, so it is this entropy of the superselection sectors which we wish to study for both electric and the gravitational field. Okay, and the second term is the usual entanglement of entropy of a region. Now, let me just summarize before we present the calculation. So what we do is we evaluate this particular edge mode contribution for a U1 theory in arbitrary d dimensions. Now, and when we evaluate it, we look for the logarithmic divergence term, which is sort of RG invariant. And we show that we see that it agrees with something called the edge Harishchandra character of U1 field on SD. Okay, SD. So if you're in D dimensions, it's SD. But the sphere is in a D, I mean, the entanglement sphere is in a D minus 2 dimensions. And we repeat the same calculation for the graviton in D equals 4. And here too, we observe that the contribution of the logarithmic divergence agrees with this Harishchandra character of spin 2 partition function in S4. And also the bulk mode is done, but I wouldn't emphasize that much, but I will talk about the bulk contributions of the entanglement. So let me just outline the U1 theory. So this is the formula as we saw. The edge is sum over PE, log PE. And we will work with a spherical entangling surface. And what is this E? This is the electric field configuration on the boundary, as I showed in a little picture. And this of a particular, you choose a particular region, and there is an electric field configurations on the sphere. And what is this PE? It's the probability distribution of this radial labeling the superselection sectors. The U1 theory is free, so the probability distribution has to be a Gaussian, whose standard deviation has to be the 2-point functions of the electric field on the sphere. So this is the answer. So P of E is a Gaussian, and if you take, for instance, the 2-point function, it will give you the radial, the 2-point function of the electric field on the sphere. So this is the P of E, and G of R is this 2-point function of the radial component of the electric field on the sphere, and N is the normalization. And if you substitute that in this particular formula for the edge modes, you get this, you just work out the algebra. So the logarithmic coefficient is basically half log the determinant of GRR. So GRR is this particular correlator, and if you evaluate the half log determinant, evaluate the log coefficient, you should be able to get the edge contribution. Now, so the strategy is straightforward. So you quantize this theory, evaluate its 2-point function, and obtain its determinant, okay, and extract the log coefficient of this. So, that will be a cutoff, log coefficient with respect to the cutoff. So, for the Maxwell's theory, the natural variable to do it is basically the harmonic. In the radial, you quantize the thing in vector harmonics. You can go ahead, we expand this in vector harmonics and fix a gauge. This is basically the tangential directions to be set to 0. You can eliminate one. Again, as expected, there will be 2 degrees of freedom after gauge fixing, AR and AM. And if you solve the wave equations, you can actually get this particular expansion. This is the similar expansion as you do in flat space, except that these are all just done in radial coordinates and so on, and therefore the Bessel functions appear. It's a very similar expansion. And then go through the algebra, canonically quantize it, and find the electric field operator on the sphere. It is related to the momentum, and then evaluate its 2-point function. Okay. It can be done. Once you do this quantization, it can be done. And if you do evaluate this, you can get it diagonal in the momentum, in the angular momentum basis. So that's the expression. Okay. So we need to evaluate the determinant of this operator. So writing this correlator in the vector harmonics is technically, though it's complicated, but it results in the simplification that the 2-point function is diagonal in the vector harmonics. And here is the answer. In the harmonics, the diagonal elements are these. And you just have to evaluate the determinant of this operator. And here it is. So it's basically 2L plus 1 into log of L into L plus 1. You can see, so you can see that that's the structure which comes in, and the degeneracy is 2L plus 1. So that's the way it is. And by looking at it, you see that the the determinant of this edge mode contribution, or the entropy of the edge mode contribution, is basically determinant of a scalar Laplacian. scalar Laplacian, and that's the one here. So one of the things about that scalar Laplacian is that you can rewrite this using a set of identities in the following form. Okay. This is just rewriting the whole scalar Laplacian in a set of identities, and you result in this particular form. And the logarithmic divergence can be extracted by just looking at the 1 by t term in this integrand. And that's 1/3 of this. So this rewriting is quite useful because, as you will see later on, this is what leads to the relations with Harishchandra characters. So this is a set of identities involved in rewriting it, and you wind up with this particular form for this for the U1 theory in 4 dimensions. Now, this method of evaluation of edge modes have been carried out by several groups, actually. We have just done it in the spherical coordinates, okay, for generalization to the graviton. And we have modified the method, actually originally developed by Soni and Trivedi, who worked actually in Cartesian coordinates. And we worked in polar coordinates in this manner. It leads to a simplification which helps us to generalize for the graviton. And they worked in the Coulomb gauge, more appropriate for the Cartesian coordinates, and performed a spherical wave decomposition towards the end to bring it in diagonal form, the 2 correlator. And their result is this. Actually, it's a little longish result. We had this in the nice, in a compact form in terms of the Legendre polynomial, in terms of the second kind. So they have it in this particular expansion. And of course, the results we have agreed term by term with this, just as a cross-check. So we compared, and they do agree. But let's just complete this. So what we did was we evaluated the edge mode. We can go ahead and evaluate the other term also. And together, this coefficients of the edge together with the bulk, okay, these are the history of various evaluations of the edge mode and the bulk term. And together, initially it was evaluated by Cassini and Huerta, and we had a different method of evaluating it. But together, together when you add the coefficients together, they become the A-type conformal anomaly. Now, this approach of quantizing it in this spherical way, expanding it in terms of vector harmonics, can be, of course, carried out to U1 theory in d dimensions. And using this, we notice the general phenomena. So this logarithmic coefficients of the edge mode, in fact, is related to this determinant of a scalar Laplacian on that sphere. Okay, and this is true for the higher dimension, Maxwell's theory in higher dimensions. We notice this by the explicit computation, and you can rewrite it in terms of this Harishchandra character. Okay, so it's in fact just a partition function. It's a transform of this Harishchandra character, and the log term can be easily extracted by it. Now, another observation is the following. Is that if you look at the U1 theory on the sphere, on the full sphere, SD sphere, and you look at its partition function. So this is the U1 determinant, right? It's a partition function of the U1 theory in an SD. When you rewrite it in terms of Harishchandra characters, okay, Harishchandra characters is basically trace over a particular karta. Okay, so if you rewrite it in terms of that, there is 2 factors to it. One which we can clearly define, identify it as a bulk, and one we can clearly look at it as the edge. Okay, so here it is. Here the first term is the bulk, and the next term is the edge. And if you do this and you keep looking at the edge, right, and the bulk also actually agrees, the edge, the coefficient of the log of the edge agrees with the explicit calculation of the entanglement entropy. So just to identify the edge contribution, one can actually just look at the U1 theory on the full sphere and rewrite it in terms of the Harishchandra character and identify the edge. Okay. That's an observation. We don't know why it's happening, but that's an observation. So with this observation, let's move to the gravitons. So the gravitons are basically, we are looking at linearized theory of gravitons. It admits this gauge symmetry. And Riemann curvature is the gauge invariant. And the equations of motion, of course, are the Einstein's equations. linearized Einstein's equations. And in case of the Maxwell theory, the Gauss law resulted in superselection sectors. Now, to obtain a gauge invariant characterization of the superselection sectors in gravity, we think of the Riemann curvature as a field strength in U1 of a U1 gauge potentials. So that's sort of known. So if you construct this particular combination, it's a combination of Christoffel connections, actually. If you construct this particular connection, you see that alpha beta is like a label, and this object transforms like a U1 vector potential under that transformation. Okay? And the curvature is basically like the field strength of that U1 potential. Now, the Hamiltonian constraints of gravity is the following. And this, together with Bianchi identity, admits a Gauss law-like description. Right? So this is like the Gauss law-like description that we saw in the U1 theory. So the curvature components are analogous to the U1 field, which is what we expected, and the Hamiltonian constraints become Gauss law constraints on that, on that curvature field. So, so therefore, the superselection sectors are basically, so let me just look at that, show that again. So here is the Gauss law constraints, and the superselection sectors are basically, the fields which are of these, which are kept, same outside and inside that particular region. So these are the superselection sectors. They're labeled by 6 components. And the strategy is similar. We follow the same strategy. So gauge fix and quantize the theory using metric fluctuations of tensor harmonics. Determine the relation between the 6 components and the gauge fixed operators which you use to quantize the theory. Like you remember we wrote the F field strength, electric field strength in terms of the momentum. And yeah, here it is, electric field strength in terms of momentum. And how much of these are local? In this case, we have to look for that because there it turned out to be local. So we find the, which are the local relations between, the curvature, which is which the Gauss law makes you constant, and relates it to the quantization variable, and then evaluate the 2-point functions. So we break up the spin field, the spin 2 field, into this various modes, basically the vector mode, tensor mode, and the scalar mode. So there are various modes, and you can actually gauge fix it. And finally, again, there are only 2 degrees of freedom. So we follow a gauge fixing procedure developed by Cassini and Veneretti. And so there are finally 2 modes, which correspond to the tensor modes, which are, and we can solve for the equations of motion. And here is the sort of similar to that U1 field expansion in terms of the radial coordinates, in terms of the Bessel functions, and so on. So there is a similar expansion which you can do. So you quantize this in tensor harmonics and find the canonical commutation relations. And before we find the correlator, we need to find out which of the 6 components determined by the Gauss law are locally related to the gauge fix modes. And we do that. So here is the relations between the various these are the variables we quantized, and these are the 2 local relations, and the rest are all non-local, which generate non-local algebras. So we look at these 2 relations, all of them are. So the remaining 4 components are non-local. So we look at these 2 particular curvature components, which are related to the the variables we use to quantize the theory, and we evaluate its 2-point functions on the sphere. And again, we can rewrite this 2-point functions in a neat way in terms of that special Legendre polynomials of the second kind, of the functions of the second kind. And there is this particular structure of the terms here. There it was L into L plus 1. Here there is this particular structure. And if you go ahead and evaluate the edge modes, we get this this particular formula. Okay. And we can evaluate using heat kernel techniques, and we get 16 by 3 log of r by epsilon. We get a coefficient number. Now, how do you know whether it is okay or not? What we do is we looked, because we saw that pattern of the partition functions on the sphere, we looked at spin 2 partition functions on the sphere. And then, we write it in terms of Harishchandra characters. And when you do that, there is this bulk part and the edge part. And here are these expressions. And if you look at the log coefficients from the edge part, it is indeed 16/3, and it agrees with that explicit direct calculation. Okay, this is sort of the handle we have on this particular calculation. And for completeness, let me present the bulk part of the entanglement entropy. And it was initially done by these authors. And later on, I think we did it using a different method, and we both agree. And together, they become this. But for this particular case, there is no understanding whether this is the anomaly, Euler type anomaly or not. But this is a contribution of both of them together. In the U1 case, there's an understanding when you put both of them together that it is a A-type anomaly. And for arbitrary spin, using all these connections, we have a formula, but we don't have this direct calculation in terms of this correlators on that sphere. But there is an expression for all of them. Now, so I talked about this graviton, and of course there is, as we saw in the initial discussion as well, there is this issues dealing with, gravitons, partitioning a particular, space and understanding entanglement entropy. But, we go ahead, we sort of understand, we try to understand whether we can study, excited states of gravitons. Okay. That was the vacuum, just understanding the vacuum entanglement. Whether we can actually create excitations in the quantum field theory using graviton, and then study its change in entanglement entropy. Now, so the theory has gravitons, right? Non-interacting gravitons, free gravitons. So that was the sort of vacuum contribution, which sort of is consistent with other calculations also. And now we sort of try to excite that with a local operator. So this is the local operator, O. This is a standard way of creating a quench here. Local operator. The excitation is carried out. So just having a picture in mind, so there is this Y. This is the Y and then this is Y. The XZ is here. And then we create an excitation at, say, Y0, and let it evolve. So let it evolve. So it evolves like a spherical wave, right? It evolves like a spherical wave and goes into this particular region and asks the question, how does the entanglement jump? We ask that question, and that's calculable, actually, using replica tricks and so on. It's calculable. So this is a surface of, Y is XZ plane here. So there is an SO2 times SO2 symmetry. And we study the time evolution of this particular disturbance coming inside and increasing the entanglement. And in particular, we wanted to study for the graviton because it has been studied for the spin 0 and spin 1. We wanted to study for the graviton because we want to see how different it is, because there's all sorts of discussions in the literature that it's very different. But we go ahead. So the nature of the excitations can be probed by evaluating the stress tensor of that density matrix. For the spin 0 and 1, but spin 2 does not admit a stress tensor, so we sort of local, gauge invariant stress tensor. So we evaluated the Kreshman scalar in that density matrix, and here is the Kreshman scalar. Just to see the picture, so this is the excitations at t is equal to 0. So there is the spike, and this at higher t it spreads out. This is one particular time, and this is a later time. The amplitude dies, and it spreads out. And, of course, it goes into this half region. Okay. And so you can evaluate the entanglement change. And what is interesting is that you can organize the entanglement change in terms of polynomials, 2 S+1 order polynomials, polynomials with, in terms of y and t. So that's the only variable you have. The y and the time at which it hits. So you can organize it in terms of those polynomials. And they can be, for each field which has some particular representations, there is a very nice polynomial structure. And we evaluated this time-dependent growth for all these components of the gravitons, as well as gauge fields. We repeated the analysis. So here is some of the nice
you have 10 minutes.
10 minutes. Oh, I went through very fast. Okay. So we have this particular case. We can come back to the discussion. So So we have this polynomials for each of those fields. And here are some plots. Okay. So once the disturbance enters this region, the entanglement jumps, and it jumps and saturates at log 2. All of them, it saturates at log 2, the various fields. And you can organize them into, as I said, into polynomials of that y by t. And there are 2s plus 1 order polynomials for the spin s. Okay. And it saturates at log 2, and there is different rates at which it saturates, which can be understood again in terms of the SO2 times SO2 representations. And the graviton is no different. I mean, in terms of at least the linearized theory, it's no different in this treatment. So here is for all the components of the graviton and the various sort of jumps. So let me just summarize. Of gauge theories, especially of gravitons, is interesting. And it's important to understand them more, because it plays a role in holography. And of course, there is all this, debates whether you can actually split a region and so on. Because of this relevance of this particular formula, which is quite important in the recent discussions of information loss, it's important to, check whether these edge modes or how exactly this definition of S bulk plays a role. Okay? And as we saw, the growth of entanglement is controlled by this simple 2s plus 1 order polynomials in this case. Okay, I will stop at this.
Yeah, Ramesh?
Yes.
Can I? Yes. Actually, I have a whole number of comments, questions, whatever.
Yeah, it's okay. I know this topic is very interesting.
I mean, the first statement is going back to what was discussed earlier. Even for a scalar field, as far as I know, the Hilbert space does not factorize. You can relate it to type 3-1H for the Neumann algebra, goes back to Riesz-Leiter theorem, whatever.
Right.
So what you're saying really is that there is an additional problem from gauge fixing.
Right.
Okay. Now, secondly, coming to the gauge fixing, there are two issues. One is there is a term that arises, the so-called contact term.
This is related to this. Yeah.
This is related.
Yeah.
So I just want to point out that that was actually evaluated already in 1994.
Yeah, by Kabat. Yeah.
By Kabat.
Kabat. Yeah, these are related. There's the same term. It's the same term. Yeah. In U1 theory.
In the U1 theory.
Yeah.
Yes. Now, if you look at the operator that enters your correlator of the electric fields on the surface, that's also called the Dirichlet-Neumann operator for the Laplace operator.
That I don't know. Okay. Yeah.
Another comment is that when you look at factorization of determinants of Laplacians, there is a formula due to Berleyer, Friedlander, and Kappeler, which tells you what is the obstruction to the factorization. And the extra surface term that appears in the formula is exactly this term that you're calculating. Okay. So there are many, many factors that come together in this.
Yes, we don't understand why that it becomes this Harishchandra character.
I think that's very, very clear if you look at the BFK formula, actually. Okay. Yeah.
But has that been done for the graviton also?
No, I'm not talking the graviton.
It's just for the U1.
It's just the U1 case. Anyway, finally, in 2+1 dimensions, you can actually do this even for the non-abelian theory.
Oh,
okay. And the U1, where it's much clearer how the factorization occurs. So that's something perhaps we can talk privately. Okay. Just want to make a bunch of comments.
Yeah, so hi Justin. So my question is related to what Parmeshwan asked. So the contact term of Kabat, I thought that is this problem that the ghost mode contributions were not included, and Donnelly and Wall showed that there's a reduction.
So actually, this is all after that correction.
Okay.
This is all after the correction of that. I agrees with Donnelly and.
I see. But then, how does the Harishchandra side know that ghost has to be? I mean, is there understanding?
No, the Harishchandra character. So when you evaluate the U1 field, on the sphere, you have to do the ghosts also.
On the S2, you mean?
On the sphere. Like the Harishchandra character, by the way, is S4.
But there also the ghost is there.
Yeah. So there so you look at S4 partition functions, and then when you write it in terms of these characters, there is this term.
So you can see the subtraction of the ghost.
Yeah.
Okay, thank
you. So the question that I had is that if the sphere were sufficiently large, then you can look at what happens for a moving charge, right? Because the charge will be inside the sphere for a fairly long enough time for you to do the calculation, let's say, right? So even if the charge is moving at constant velocity, which for example is allowed for the charge to move, would you be able to, I mean, I imagine that in that case, the PAs that you have will get
so this,
recalculated.
Yeah, we don't have, like in this theories we are doing, we are not including matter. So it's just,
so what is the,
so it's just pure, pure vacuum of just
there's
no matter. It's
okay,
just,
so maybe I misunderstood you right from the start. What is the electric field that is there on the surface of the sphere? Is that a charge that is inside?
No.
There's nothing inside?
Nothing inside.
Okay.
Yeah, edge mode. Yeah.
Just, okay.
So far as I can understand, you have not included, this is linearized gravity.
Linearized gravity, yeah.
So there is no diffeomorphism invariance.
Not the full,
so it is simply a spin to massless particle.
Right, yeah.
There is also already a paper by Brunetti, Longo and Guido and Longo that the moment you give the Wigner representation, then the localized Weil algebra can be written and the entire localized algebra can be constructed. And they show how the Lorentz group moves it from region to region and what happens when two of them cross. So causal diamond you can go. They have done it completely. And the typology is again type 3-1. Okay, it doesn't matter. The type 3-1 character of these things is because it is like symmetry of all theories of a particular character. So it is true of all quantum field, local causal quantum field theories obeying the Hawk-Hasler axioms. So, and what I want to say is, it is not clear to me how this calculation is encompassed in that. For example, today's Longo paper, he gets a finite entropy, and that is because of the split property, which there is a long literature.
So, I mean, let me understand my words. So, this paper, which the Longo paper you're saying, is that for linearized gravity, it is similar to other quantum field theories. Is that
all they have actually quantized all Wigner representations because of the existence of Hilbert space. That's it. Okay. Once you give the Hilbert space, they can write down the localized Weil algebra, which is all bounded operators, and they are of a universal character, and they can construct. Then they move it by the Lorentz group, which is an outer automorphism. Then they do the calculations, and that's a very beautiful.
They have done similar calculations. I can compare the results with. Right? I mean,
today's paper is doing something else. The point is, if you have a causal diamond, and you take the causal complement, it can touch at the edge. If there is a touching and you try to compute the relative entropy using Tomita Takesaki modular operator, relative modular operator, it diverges. Okay? There is a universal divergence depending on because of the point of contact, and there is also a universal property if you split it a little bit, epsilon distance. So then you have a logarithmic divergence which is universal. Okay?
Universal.
And today's paper, from what this is, I have only.
Do they compute the coefficient?
They find the coefficient which is universal, and they calculate it, and they clarify what the situation is.
So if they have the number, I can compare against it.
I think there is a number. I don't know. Then there is this business of DS. So people have been talking.
DS.
I should say I'm discombobulated. It has horizons. Observer horizons. So it is not at all trivial to make a quantum field theory on that. And this paper of Ed Witten, again Roberto Longo and Chandrasekharan, addresses this issue. So they take one Rilder wedge or the digital space and a complement, and they try to ask, can I trace out the complement as an observer which you are missing? Okay? And they change the type 3-1 by introducing new operators, then it becomes type 2-1. Type 2-1 has an entropy, but it has no minimum entropy. It has a density matrix. but there is no minimum one. There is a maximum one with a maximum entropy. That is unique. So they calculate it and say that it is the same as the Hawking-Gibbons entropy. That is what that
That's the
paper
black
says.
hole entropy.
So none of them uses this technology.
Okay.
Just one last comment, then I stop. It is not clear to me what is meant by restricting a field on an edge. For example, if I take, let's say, smooth functions on a sphere.
Right.
Take all, it is a seasonal algebra. Okay? I want to restrict it on the horizon, on the equator. Can I do it? Is it a subalgebra of the original one? It is not, because you need delta functions.
Need delta functions.
So what normally is done is this Koszul decomposition. So you take all algebra all functions, take the functions vanishing at the equator, and quotient it. Then you get an equivalence class. That's a set. It's not a what, it's a set. So you get some cohomology, Koszul cohomology. This is a BRST cohomology. You get them. So since you started talking, the only way to transfer it to quantum fields, which are distributions, is to smear with test functions, which are on the whole sphere. Take those which are defined on the equator and smear them and see if you can quotient it. But I don't know whether you can quotient it because it has to be two-sided ideal. So that I don't know. Okay? Because you were raising this, I don't know what to do. Okay? So it is not very clear to me what is happening here. And also gauge fixing. The this gauge fixing, just as a large comment, is coming because already Weinberg shows that for photons, this gauge transformation is coming because of a lack of an intertwiner between the Wigner representation and quantum fields, local. Okay? And that leads to indefinite metric spaces. So recent papers, the latest one I know is Mundrer and Schroer, construct what they call string localized fields. Okay? And they are acting entirely on a Hilbert space. There is no indefinite metric space at all. Okay? There is no gauge fixing. So what happens is that these fields get defined on a de Sitter cone from a point. Okay? You take all space-like directions from a point, and they write Bessel lines, and then they make completely gauge invariant operators using this. Then what happens is, to me, very astonishing. You get uncountably many supersession sectors. And, yeah, I'll stop.
Okay. So let's thank the speaker again. And there are a couple of announcements before you go.
Just one announcement. There'll be a conference dinner at 7:30 on the first floor of the canteen. So you're all invited. Please do come. Conference dinner, Bal, in your honor. Please do come. Yeah. Thank you. Lunch will be outside.
Okay, that's it. Thank you.
Zoom টাকা
Hello? But can you put it just to chat a bit?
She said she will come around after 10 minutes.
Ah, okay, fine.
1:45?
Yes,
That's
it's
what
fine.
Sujit
We
told.
make, yes, we make some proofs.
Yeah.
And,
Just what I said.
Hi, Elisa? Hi, it is Andres here talking. How are you? Yes. So,
We'll just put the microphone there.
okay. They will put you on the loudspeaker so that we can hear you better. So I guess we can just make some proof now.
Yes, try the sharing, I guess.
Yes, yes.
Okay.
So the main problem has been the sharing of screen. So maybe we can try that.
Okay, I can try. Let me try. Share screen. Yes, desktop here. Okay, now it is share.
It is sharing. Yes. And now, are you using some pointer? Yes. Okay, we can see the pointer. It's fine. So everything seems to be working just fine. So you can hear my voice, no problem?
Now she's muted herself.
Oh, we lost your voice.
She has muted herself.
Huh?
She has muted herself.
Yes, apparently you have mute on your voice. Something happened. We stopped hearing you.
Okay, is it okay now?
Yes, it is okay, just fine.
Okay, so I don't know what happened.
Okay, so
And the screen, it muted it, I don't know why. Okay,
yes.
so it seems to work everything. Okay, I can just go to the first. Okay, no, the only thing that is not okay now is going back and forth, right? Okay.
Yes.
Okay.
Okay.
Shall I unshare it now, or you want me to leave it there, as you prefer?
You can leave it there, yes.
Okay.
Now the talk will begin at 2 o'clock, but we have two clocks which are not synchronized here, so.
This one is slow.
So, yes, so in 20 minutes we begin.
Okay.
The talk is about 40 minutes with, I mean, 35 plus 5 questions, more or less. So do you want me to tell you something about the time 10 minutes before, or?
Yes, 10 minutes before the end, maybe. Okay, I will try to pay attention to that, but it would be nice if you could tell me,
Okay.
I mean,
maybe,
at 25.
maybe I will, okay, maybe I will have to interrupt you because you cannot see me, no, but
Okay,
never
fine.
mind.
I can try it. Okay, yes, sure. No problem. Okay.
Okay.
Very
Okay,
good.
Elisa.
Okay.
Nice seeing you. So,
Okay.
so see you in 20 minutes.
So I will close the microphone and I will just be out for a couple of minutes, then I will be back here.
Yes,
Okay?
I don't know if Alessandro is online. Maybe we can, or well, I mean.
I don't know. I see is connected,
there?
but I don't know if he's actually there.
Okay.
Yes.
Is there?
Okay. So we'll be back in 2 minutes, okay?
Okay, fine. Hi, Alessandro, can you hear me? What? We will see.
He's online, but he is not. Ask him to unmute and all, but he is not responding. So, I make him co-host also. Right, sir? நம்ம மாதிரி நம்ம 12 மணி நேரம் 5 மணி நேரம் இருப்போம்
Ciao Elisa, buongiorno. Buon anno nuovo, anche se ce lo diciamo in italiano.
Eccomi, ciao, buongiorno. Scusa, non riuscivo a fare unmute. Buongiorno.
Hi, Alessandro. Can you hear me?
Good morning. Yes, I can. And now I can also activate my screen. Yeah.
Yes. Okay. Let us try sharing your screen to see if it works.
I will remove mine so that, okay.
Okay. Now let me go to full screen.
Checking, just proof.
Let me just. I don't know whether it's enough or not.
Down below.
Yeah. Elisa, tu hai idea di...
Dimmi.
No, nel senso che come si fa a condividere? Cioè,
Non c'è, dove
Dimmi.
c'hai tutti i comandi, non c'è un condividi schermo, share screen, dovrebbe essere un pulsantino verde.
Sì, no, ce l'ho, figurati. È solo che...
Quando
che devo
dopo ti vengono fuori tutte le finestre.
Sì, e io abilito desktop 1, solo che poi sostanzialmente mi dice
Prova adesso.
che devo sto facendo, solo che mi dice che devo consentire a Zoom di condividere lo schermo.
Ah, digli di sì.
Figurati, diciamo.
E non c'è un continuo a qualcosa? O...
Apri preferenze di sistema. Definisci. Scegli schermo Zoom. Sto giocando con Zoom, aspetta, proviamo qui. Zoom, preferenze, impostazioni. Allora, accessibilità. Attenua, avvisi lettore, tasti di scelta. Condividi schermo. Proviamo così. Adesso
Sta
lo vedete?
arrivando. Sì. Yes,
Okay.
now it's
Yes.
working.
It
It seems now it's working. Okay.
Yeah. So we now see a screen, but not the slides.
Yeah. Now let me. How is it now?
No, I think you have the file on a different screen if you have multiple screens on your set up on your computer. Not yet. We see like a snow background, something of this kind.
No, now I close all other applications and I open only the PDF reader.
Try to go also full screen. Let's see.
It's something like that. Okay. Allora. Let me just do it here. Let's see.
Still, we see only the desktop, not the.
Yeah, the desktop.
Not the. No.
But it seems to me now I have my PDF slides on my screen, and it says that sharing the screen, but it seems that you do not read my screen.
Are you sharing the whole screen?
Sorry?
Are you sharing the whole screen?
I'm sharing the whole.
Because you can try sharing only the PDF.
The Windows.
That might work.
Let's try.
Yes.
The problem is that I don't know how to share only one file, because now I am in share mode.
When you do share screen, you should see different windows. You have to choose whether to share the whole screen or just one file and so on. And then you can choose what to do.
Hello?
Yeah.
Disconnect the screen share and try to share only PDF. If you click that screen share, it will come full screen and Adobe or something you using, right? Preview or something. It will come. Disconnect this one screen share.
Stop the screen share.
Stop the screen share.
Let me stop.
Now click the share screen.
On the right.
Yeah, you need to open the PDF. He said he already seen the. No.
I don't know what you see now.
You see just the background screen.
Okay.
Yeah, which is completely empty.
But I mean, my screen is not empty, so.
Alessandro, sorry, I just speak one moment in Italian, and maybe we can understand.
Yeah, fine,
better.
please.
Quando fai lo screen sharing non ti vengono fuori tanti quadratini e tu decidi quale di quelli condividere?
Allora mi viene un desktop 1, un lavagna, iPhone e poi questo.
Non c'è solo il PDF da condividere?
E prima provo con questo.
Perché dovrebbe essere possibile condividere o tutto lo schermo o i singoli file che tu hai aperti, però li devi avere già aperto sullo schermo. Ecco, adesso vediamo. Ok, now we see.
Now we can see it.
Yes.
Great.
So now you see the PDF file.
Yes.
We see the whole desktop and the PDF, so we should go full screen.
I simply go to full screen mode. How does it look now?
Perfect, great. Okay.
Good.
So
Thanks a lot for the remote support.
Okay. So we start in 1 minute, 2 minutes. Okay. Now you have to unshare screen so that Elisa can share hers.
I will share it again, okay?
I did it.
Is it fine?
Yes.
Good. And you see going forward, right?
Yes. Just fine.
Okay.
Okay. Just a minute, we are calling people to get into the
Sure,
room.
sure. No problem. You let me know when you're ready.
Fine. Okay, hello everybody. We are ready to begin today's afternoon session with Professor Elisa Ercolesi from the University of Bologna, and she is going to talk about quantum simulations for abelian gauge theories. So, welcome, Elisa.
Thank you very much. Let me start by thanking you all for, and the organizers in particular, for inviting me to give this talk in honor of Bal. And let me also say hello to Bal, that I saw him passing before. And just a couple of words before starting. I was a PhD student in Syracuse from 90 to 94. And that was really a great period. And it was the period when we started working on post-sets and their algebras that we discuss with the tools of Conson on commutative geometry. During that period, I met in Syracuse excellent researchers and colleagues who are now also very good friends. And I think many of them are actually here and taking part to this nice fest. Those years were for me years of very intense learning and very lively discussion that, as most of you might know, happened at every afternoon in room 316. And that actually shaped my way of studying and making research really a lot. So for all that, I'm really very grateful to Bal for his teaching and friendship in those years and even now. So I'm really honored to be here. And let me thank, first of all, Bal for all his efforts and work in all these years. So what I'd like to do today is to describe you some recent lines of research that we have been doing in Bologna in collaboration with many other groups that have to do with the quantum simulation of abelian, and somehow I will say just a couple of words about non-abelian gate theories at the end. Just to start with a very quick outline. And the idea that I'd like to outline you how we can go, when talking about simulation lattice gate theories, how we can go from classical to quantum algorithms to simulate field theories. The main ingredient here that I'll try to discuss a little bit is a quantum many-body Hamiltonian. Let's say in contrast with what happens with standard classical simulation of lattice gate theories in which you usually use the action, okay? And the goal of all this stuff is to actually be able to perform simulation of non-perturbative phenomena, so simulations that are able to take into account non-perturbative phenomena, and also describe dynamical or out of equilibrium phenomena. So the first step in all that will be the calculation of the many-body ground state of the Hamiltonian with sufficiently high precision. And that will be done, can be done either by a fully, let's call it digital or hybrid, as I will describe you, variational approaches that can be implemented on quantum computers. And I will comment on that at the very end. Actually, the idea of using quantum computers is quite old. The first time I think people talk about that was by Feynman in a seminal talk and paper at the first conference on physics and computation at MIT in 1982. Actually, for the first time, he discussed the fact that we do need quantum computers in order to be able to do an exact simulation of nature, since nature is quantum. So he was the very first one who put forward the idea that we do need quantum computers to be able to do exact simulations of physics. And indeed, that was just the beginning of a long history of actually classical simulation of quantum theories on classical computers, including field theory and gate theories that that reached big successes. So we don't need to remember the whole great effort that we made to simulate field theories and in particular lattice, gauge theories on a lattice. But so this is an old story in some respects. So what's new about that? Why to care still about that? The idea that now we are in the era which we are starting to see real quantum computers. So there are big companies like D-Wave, IBM, Google, and so on that are really building and putting at research disposal platforms that are able to perform quantum computations. And, but the same is actually happening in many research labs worldwide in academics, as well as now we have startups like the one that you see here, Pascal in France, for example, that was founded by the Nobel Prize Aspect a few years ago, that are actually putting on the market quantum computers. So the idea is, what can we do with that now? And this is actually a very exciting field at the moment, because it's actually putting together different ways of looking at the physical theories. It's putting together high energy field theory of fundamental interactions, for example, with the study of quantum anybody Hamiltonians on discrete space, therefore on lattices, together with the physics of synthetic platforms that are using, for example, spins or cold atoms and ions as platforms where to actually make the simulation, the real simulations. And these platforms are actually very versatile, and so they can be adapted for simulation of very different models. There is a lot of efforts, for example, to make simulation of chemical compounds and condensed matter models, which somehow are the natural ones to consider, but also more complicated statistical mechanics models and critical phenomena can be tackled from this point of view. And as I will try to convince you, and there is also a lot of research in that field, fundamental interactions can also be studied in this context by looking, for example, at particle physics or even gravity. And this is, for example, a review paper that came out a couple of years ago, and the idea is that these techniques will hopefully will allow us to consider non-perturbative effects, to study, to simulate non-perturbative effects, together also with real-time dynamics and out of equilibrium situation for these models, which is really the new frontier of these fields. So here in Bologna, we started in collaboration with many different projects on that. I'm not going to describe them all. I just want to say that there is at least, I mean, worldwide and also in Europe, a big business about this stuff now. And so to start with, let me describe you the beginning of this story, as far as we are concerned, which resulted in a work in collaboration with Giuseppe Marmo and Paolo Facca and Saverio Pascazio in Bari, and several other young PhD students and postdocs. And the first model we considered was actually a discretized version of quantum electrodynamics in one dimension, or the Schwinger model, if you want. And when I talk about one dimension, I mean one special dimension plus time. We are using a Hamiltonian approach, so time for us will always be continuous. And what we really need to do is, first of all, to discretize on the lattice the continuum Hamiltonian of the Schwinger model that you see here, which has a U1 gauge group. And it contains, as you can see, the standard electromagnetic energy, which in one dimension is just given by E square. And then we have the coupling of the matter field psi. We're talking here about spinless fermions. I don't put the spin, it can be added if one wants, with the gauge potential through the standard covariant derivative. And of course, you also have to take into account Gauss law. Then, as usual, we discretize time. No, we do not discretize time, we discretize only space, which is replaced by a regular lattice. And as usual, we have fermions defined on lattice sides, whereas the gauge fields will be defined on links. So also, let me start from the gauge fields, which are easier. So the electric field will be defined just on a couple x plus 1 of sides. And this conjugate variable will be considered, that we consider here, is actually the exponential of the gauge field A, which is what we call the comparator. And whereas the fermions, as I said, are put on the sides of the lattice, and we are using Schwinger's staggered fermion suggestion to avoid problems like fermion doubling, for example. So we actually split each physical site J into even and odd site, x plus 1, on which we put the positive and negative energy solutions respectively. So in this way, each physical sites contain 4 states. The direct vacuum, in which we put a charge only on the odd site, which is occupied by negative energy solutions. Then we have the quark, what we is called the quark in the literature, which is by putting a charge on the even site, positive energy solution. Then we have an anti-quark by removing the charge from the odd site. And then we have the meson, which consists in a quark, anti-quark, or particle-antiparticle couple. So each physical site actually contains all these 4 states, which, if you want, are the basis of our local Hilbert space. Then we want to go quantum, okay? So let's describe what we have to do. And in order to go quantum, so to be able to also perform this calculation on a computer, we need also to discretize, but not only discretize, but also to make finite the degrees of freedom of the electromagnetic field that lies on each single link. And in order to do so, we go to a value quantization scheme in which we use the comparator, which is exponential of the gauge potential A, together with the operator that we denote here with V, which is exponential of the electric field, because the algebra of these satisfied by these this pair of conjugate variables is actually admits unitary finite representation of dimension n, which means that we can, on each link, we have a finite dimensional Hilbert space, which is generated, therefore, by n basis vectors, which on which we can act with V and U in a very simple way. The basis here, which is called the electric basis, is chosen in such a way that the V operator, therefore the exponential of E, is simply a multiplication by phase, which is 2 pi over n times k, whereas the U operator acts as a shift operator, actually a cyclic shift operator. So what really we are doing here is to substitute, to have a discretized quantum electrodynamics models in which we have fermions on the sites, and on the links we have an electric field which is characterized by a discrete and finite number of variables, which are given by 2 pi, by multiples of 2 pi over n, and therefore we have the then discrete lattice gauge theories. And if you work out in detail the Hamiltonian that you can get from the Schwinger model, it is the one that is given here. So we have the standard kinetic part in which the covariant derivative has been replaced by the U comparator operator. Then we have the stagger mass term due to the Schwinger approach. And then finally, we have the energy of the electric field. And let me just stress that we have 2 parameters in this Hamiltonian. One is the mass, and the other one is the coupling G of the electromagnetic field. And so the idea that with this Hamiltonian at hand, we are able to perform simulation in a classical computer of different situations. What I would like to concentrate on is on some dynamical properties of these Hamiltonians, on some dynamics. And in particular, I will concentrate on the possibility to produce mesons, so particle-antiparticle pairs, and on the dynamical behavior of a string state. A string state is a state in which we create a particle out of the Dirac vacuum. So on the left, on the right, we have just the Dirac vacuum. We create a string, meaning that we create a particle on the left and antiparticle on the right. So we have a non-zero electric field in between. And we want to observe the dynamic of such a string for different values of the mass and the coupling constant G that was appearing here. Here is just a picture for Z3, for example. Okay, so let me just give you the result of our simulation. We did a simulation here using classical algorithm, in particular with the time-dependent density matrix renormalization group algorithm. And I'm just going to show you the result that we obtained for Z3, but we did the same for Z4, Z5, and we can just go on. And we studied two interesting dynamical problems. The first one is spontaneous pair production. So the idea is that we are actually using what we call a quench protocol. So we prepare the system in the Dirac vacuum, which is actually the ground state for very large mass of the system. And then we let it evolve freely with respect to Hamiltonian, which has some fixed value of M and G, okay? Which is not, so in this case, the Dirac vacuum is not the ground state of such Hamiltonian, and so it will evolve, and what can happen is that we have a spontaneous production of particle-antiparticle pairs, and that is indeed what we want to check. So the first graph that you see here is actually the average particle density of all over the chain. So, okay. So we start from 0, which corresponds to the Dirac vacuum, and then you see that as the time evolves, we have a non-zero particle density that arises from spontaneous pair production. And you see a first sort of linear term here, which is actually what also was predicted and studied by Schwinger in an old paper. And then you see that as time goes on, we see oscillation. So we have interference effects among the different pairs that are produced. And then we have all these oscillations here. And we calculated this quantity, because actually this quantity was measured in a very nice experiment using cold atoms. So this is an example of a very first experiment that happened in 2016, and then there are new refinements of that, in which people used cold atoms to build a quantum simulator for that. So just to see you that indeed there's experimental result using cold atoms as a quantum analog computers works quite nicely. And I also would like to show you some interesting results that we got by going from the weak coupling regime to the strong coupling regime by increasing the mass of our particles. And that, for example, can be seen by looking at density-density correlation, so by looking at correlation among particles. The first graph on the left, you see density-density correlation as they evolve with time, okay? In the case of in the weak regime, the mass is very small, very close to actually the confinement transition, and you see that the correlation starts to develop after a short time when pair production occurs, and then correlations will tend to spread all over the chain. On the vertical side, you have the size of the chain, following a sort of light cone direction, okay? On the contrary, when we go to very strong interactions, M here is much larger, you see that actually correlation are not longer allowed to spread freely inside the chain. And you see this recursive phenomena, which is somehow also dictated by this oscillatory behavior that you see in the average particle density. So correlations are no longer able to spread all over the chain. They remain confined in the center of the chain, and they have this periodic, very strongly periodic behavior, which is something quite unusual to see. And these kind of unusual results come out also if you look at stream breaking. And so what we really want to see is to to see if we prepare the system in a string state to study if the string breaks into smaller strings as time evolves or not. And in fact, we see that we can see three different regimes, three different dynamical regimes by following real-time dynamics of the string. So we start at t equals 0 by preparing the string as a center of our chain. It is the color here represents the electric field. So you see that the electric field is concentrated only in the middle of the chain. And then when we are in the weak regime, M and G are both small, the system will evolve into a first phase in which we have a breaking of the big string into smaller strings, which are mesons, couples of particle anti-particle pairs in nearby, okay? And then interference effect will make this state evolve into a system in which we have two mesons at the end of a sort of light cone that we will spread moving toward the edges of the chain. This is what happens in the weak coupling regime. We have a breaking of the chain and spreading of the excitations. On the contrary, in an intermediate coupling regime, we do see a breaking of the string into smaller strings, which are couples, pairs of particle-antiparticles, but we do not see any longer the spreading of the excitations. And until we reach a very strong coupling regime, in which actually the string does not spread, but also does not breaks into smaller strings. So we are able, by following different dynamical evolution, depending on the regimes of the coupling constant in which we are. And that can be simulated very easily in this approach. So this is, as I was saying, done using our approach of a, let's say, quantum Hamiltonian on a lattice, but using just classical algorithms, in this case, the DMRG algorithm, to study time evolution of our system. Now I would like to move to describe what we can think to do on a quantum computer. Okay, and so I would like to describe you how we can actually develop a quantum algorithm to describe the physics of lattice gate theories. And in this case, I will concentrate on the simplest one, which is just a pure lattice gate theory, so no matter added here. I will work in 2 dimensions, and I will take the simplest discrete group that I can think of, which is Z2. So in this case, our Hamiltonian is just defined on variables that are defined on the links, which are our field, gauge fields variables, which are just 2 states, because we are looking at Z2. So I will take these 2 states as given by the plus or minus states of the X Pauli matrix. So this is a Hilbert space on each link, just 2-dimensional Hilbert space. And then the Hamiltonian we are considering consists of an electric part, which is just proportional to sigma x. So these plus or minus states are exactly the eigenstates of the Hamiltonian, of the electric part of our Hamiltonian. Of course, this electric part will contain the sum over all possible links in our 2-dimensional lattice. And then we have a magnetic contribution, which is built up as usual using plaquettes. And here we take the product of the sigma Z matrix, which does not commute with sigma X, on the 4 links that are making up an elementary plaquette that here I'm calling BP. So this is the standard way we write down the magnetic part contribution, and the total Hamiltonian is the sum of these 2 parts weighted by the coefficients H. And of course, we can also write down the Gauss law here, which is just related to the application of sigma X matrices on all links. Okay, so this Hamiltonian, we know the analytical ground state in 2 limits of this Hamiltonian in 2 limits. One is electric field limit in which H goes to 0, and that, as we said, is just the tensor product of the state plus on all links. And we also know the exact ground state in what we call the magnetic limit, which corresponds to H going to infinity, because the Hamiltonian I've just described actually goes into the so-called toric code Hamiltonian. And so the ground state here, the exact ground state is just an evenly weighted superposition of all possible Wilson loops, closed loops, applied to the electric field state. Okay, so these are the two reference states that we're using in the two different limits. And it is well known that the Hamiltonian we just discussed actually has phase transition, quantum phase transition at the value of the H field, which is about 3, and that the system is described by a confined phase when H is smaller than HC, whereas it is in a deconfined phase when H is greater than HC, and indeed this is a topological phase. It is in the same class of universality than the toric code. And this is what actually we would like to check with our quantum algorithm. So the algorithm I'm going to propose you is known as QAOA, or Quantum Approximate Optimization Algorithm, and it's actually not a purely quantum, a fully quantum, but it is a hybrid classical quantum protocol. And we have decided to use a hybrid classical quantum protocol because the technology of quantum computers that we have at our disposal now seems to be to perform better if you are using hybrid classical quantum hybrid protocols. I can discuss with that about that later, maybe answering questions if you have. And let me just describe it a little bit. The idea is to exploit the powerful of quantum computation to prepare the ground state of our Hamiltonian. So we actually have a quantum part in our protocol that uses a quantum computer for quantum preparation. So starting from some initial state, we use a quantum circuit, which is parameterized by some evolution angle that I'm just calling here in this picture theta, that will prepare for me a variational ground state. Okay, we choose which kind of variational ground state to prepare. We make up a quantum circuit that does prepare this state. And then we use the quantum circuit also to make a measurement of the mean value of the Hamiltonian on this parameterized quantum state, variational quantum state. And then we will update the parameters we use in our quantum circuit by optimizing the value of the energy, which means to minimize energy, using now a classical protocol. So we just use a classical algorithm to minimize the energy, and that will give us the better circuit that is actually able to prepare the ground state of the system. This is what is called the quantum approximate optimization algorithm, and it has been shown to be quite effective in in different kinds of problems. And for the first time, we try to apply that to lattice gate theories. So
Elisa?
let me just sketch. Yes, sir?
You still have 10 minutes.
Perfect, okay. And let me just sketch very quickly the steps of this protocol. I'm not going into the details. I can answer questions if you have at the end. So we decided to use as initial state either the electric ground state or the magnetic ground state, the two ones that I described to you. The second one is more complicated to prepare, but it can be done. And as you can imagine, it might be more efficient when we are in the regime of strong magnetic fields. And then once we have chosen the initial state, psi 0, either the electric or the magnetic state, here I'm just annotating with psi 0, we need to construct the parameterized quantum evolution, which will be then implemented by the quantum circuit. We use a Suzuki trotter-like decomposition. So starting from psi 0, we evolve it by using the exponential of the two pieces of our Hamiltonian, HE and HB, by making unitary evolution, starting from psi 0, in at different levels, so use P levels. Here, P is an integer number that is denoting how many steps we are using in our protocols. And the rationale of all that is that increasing P, we will able to explore more and more with better and better precision the whole Hilbert space by letting evolve psi 0 with more and more of these individual pieces. And the idea is that we are able to construct a quantum circuit, quantum gates and a quantum circuit that are actually able to implement each step of this Suzuki-Trotter decomposition, so that we will be able to prepare this state by using a quantum computer. Just to give you an idea, the quantum circuit is very simple if you want, when you want to implement the unitary operator that corresponds to the evolution by means of the electric part. Here, the electric part is essentially sigma x, so it's simply the unitary evolution, which is exponential of sigma x, and it's just very simple circuit that needs to be applied to each state of each link, P1, P2, P3, and P4 for a plaquette, for example. The situation is slightly more complicated for the magnetic part evolution. We do also have a unitary operator, which is exponential of sigma z, but we have to combine the evolution of all links by means of this operator in a more complicated way, because we need to act on a plaquette, so 4 links all at once. And the idea is that we can evolve this, for example, this vertical link by taking into consideration what is the state of the other 3 links of the plaquette. So it's actually conditional evolution, which can, however, be implemented in not a too complicated way by means of this single gate unitary evolution plus conditional gains like C-naughts. And this is a picture, for example, of the evolution of 2 plaquettes like here. And so the quantum circuit can be prepared to construct the state. And at the very end, therefore, we end up with an variational ground state that we call psi p. We, as I said, evaluate the expectation value of the Hamiltonian, of the total Hamiltonian of the state, finding an energy landscape, which is a function of the variational parameters gamma and beta that I was describing before. And then we will use a classical optimization protocol to minimize the energy and find what are the best values of gamma of beta for the preparation of the variational ground state. The problem here is actually the energy landscape can be very wild somehow. It can be very rugged, for example. You can even have barren plateaus, which means that there are regions in which it is completely flat and it is different from 0, only very small region of the parameter space. And so it's not easy. So classical optimization has to be considered in a very careful way, but I'm not going to enter this result. Let me just show you some of the results that we obtained. The first thing that we checked was the accuracy of our treatment. Okay, and in order to do so, we did a simulation of our quantum algorithm on a classical computer. And in order to check the accuracy or the fidelity, we just calculated the overlap of the variational ground state, omega psi of p, that we calculated with the ground state, the exact ground state of the Hamiltonian that can be calculated by other numerical techniques. And what you see here, let me concentrate on the left, for example, is the infidelity, so 1 minus this quantity, as a function of different magnetic fields, H, values of a magnetic field, H, different colors with these curves, and in how many steps using the algorithm. And as you can see that as we increase the number of steps, we do increase the accuracy of our algorithm, which is measured by 1 minus f. And of course, the accuracy gets worse as we increase the strength of the magnetic part if we start from, as we have done here on the left, from the electric field initial state. Okay, but also when the electric field becomes 5, which is quite a strong value, the purple curve, you see that after 6 steps, we are actually able to reach an accuracy which is better than 10 to the minus 3. So it's not so difficult to have very high accuracy here. And once we have checked the ground state we have prepared is actually good, okay, we can go and calculate physical quantities. So here, for example, I'm showing you the graph of Wilson loops that are actually able to detect the phase transition, which, as I told you, happens at h around 3, because Wilson loop will start to go from a area low region to a perimeter low region that correspond to the confined and the deconfined phase respectively. And for example, if you look at the big graph here, we are going to show the Wilson loop ratio as it is defined here, which is a good quantity because we don't have to worry about the non-universal constant that appear in front of the formula of the Wilson loop. And you can see very well that our result can detect the phase transition from an area to a perimeter low very, very nicely. And lastly, there is another last result I would like to show you. As I told you, in the H going to infinity limit, we recover an toric code Hamiltonian. So, and we are in the universality class of the ground state of the toric code, which is a topological model, okay? So what we wanted to check is also the value of the topological entropy. The topological entropy is defined by choosing a three-partition of a region. So we chose the one that is shown here. So the rectangle that contains these 6 links is actually divided into the 3 parts A, B, C with two sides, 2 links each. And the topological entropy is actually defined as is shown here, where S is the standard von Neumann entanglement entropy. In particular, the full von Neumann entanglement entropy is just the last piece, SABC, which corresponds to taking the von Neumann entropy of the full rectangle by tracing out the whole rest of the system, okay? And indeed, the graph here shows the result for both the entanglement entropy and the topological entropy. The topological entropy is the green line, and which interpolates very well from the 2 known analytical results, which are 0 when H is equal to 0 because the system is in a factorizable state, to 1 in units of log of 2, okay? Because in the toric code topological entropy is actually minus log 2, okay? And as you can see, the numerical calculation that we do indeed reproduce this very well. Just final remarks. We are working now to extend these ideas to many more situations, to higher hand models. For example, n equals 3 and n equals 4 can be easily done and simulated. We are working on addition of matter, as I showed you in the sort of in the Schwinger model, for example. And we are also working, there should be a paper coming out very quick, in just a short time, to study the same kind of model, but for non-abelian discrete and finite groups, such as, for example, Dn. And what we are working now, thanks to a collaboration of INFN with the CERN and IBM, to be able to actually to really perform these calculations on the real IBM computer, to which we have access now. Okay, well, thank you again to all of you for your attention, and thanks to BAL for everything.
Well, thank you very much. Kumar?
Hello, Elisa. This is Kumar.
Hi. Hi. Nice to see you. I don't see you, but nice to hear you. Okay.
Right. Thanks for the talk. I have a question regarding the first part of your talk.
Sure.
So, when you were looking at this Schwinger model, you said, yeah, right. So, you used DMRG. So,
yes.
I mean, I was wondering, can you also calculate the entanglement entropy here using some method?
Yeah,
like
yeah,
ITBD,
sure. I've
or
not
for
shown it
example,
here, but we have a very similar plot.
Do you
For
have the
example, for
plot?
the
Can you show?
I might have it. I don't know. Let me see if I put it in the backup material. I think it's not. But it has actually, again, oscillations. So let me just to describe. Actually, the entanglement entropy has different behavior depending if you are in the weak or strong coupling regime.
Right.
If you are in the weak regime, you have a monotonically increasing entanglement entropy with the linear first part, as it is predicted by actually conformal field theory. But then if you are in the strong regime, so like here, for example, for m equal 4, then you start to see oscillations. And oscillations are stronger and stronger as you enter as you go deeper in the strong coupling regime.
And did you try that for different quench protocols or just for single? I mean, just some.
I mean, this is just a sudden quench, okay?
Yeah,
so we are actually switching from the Dirac vacuum to the evolution of, we have not tried, let's say, not sudden quench protocols like the one that are used, for example, to study Kibble-Zurek mechanisms in this kind. No, that we have not tried.
And my last question is that could you use something like ITBD in this case for that kind of analysis?
Yes, sure. Yeah, just you can.
Would that change the result from the DMRG? That's my question.
Why do you think it should change the result?
I'm asking, will it, for example?
No, I don't think so. I hope not. Okay, it's no.
Okay.
I mean, we tried. We did a small calculation using exact diagonalization up to the length. I mean, just to give you an idea, here we are able to reach hundreds of sites. Okay. And the convergence to the thermodynamic limit is quite fast. So we check that in static situations, not dynamical. And there is, whereas for exact simulation, we can go just to 20 sites at most, okay? And actually here, the point that we didn't want to stick only to Z2, we wanted to go here, the result I'm showing here are done for that, the one for Z3, but actually we went up to Z7 because we wanted also to check the limit in which the n of the Zn approximation of the U1 symmetry was going to infinity. So we wanted to recover the U1 results of the Schwinger model that indeed we managed to do.
Okay, thank you very much.
Well, are there more questions? I would have just a small question regarding the Schwinger model. When you showed this picture of the string splitting in time.
Yes, here, okay.
So is there a kind of phase diagram that you can get if you study more situations?
Yes, actually, by just looking at the string, we have it in the paper. I don't think I have it here in the backup slides. We did a sort of phase diagram as a function of M and G, okay? And we don't really have a phase transition, let's say like that. We have crossover regions that go from one to the other regions, okay? So we actually have a region when M and G are small, which correspond to this, let's say, completely breaking and spreading of the excitations, and then an intermediate region that we call intermediate coupling region in which that happens. And also you can see that actually what really matters in all that is a sort of ratio of M over G, okay? Because those are the two parameters that appear in the Hamiltonian. And then in the very strong coupling regime, we have the third one. But we don't really see sudden or abrupt changes from one to the other region, from one region to the other. And we see more like a crossover kind of behavior.
Okay, thank you. Sachin?
Hi, Elisa, this is Sachin.
Hi, nice to hear you.
Yeah. So, is there do you have any physical understanding of why the string is stable at strong coupling?
I think that what's really happening here is confinement, okay? So the idea that you have for some reason here, the interaction is so strong that we are not even allowed to make a particle move a little bit in nearby sites. And they are just kept there. But I actually agree, this is actually quite very interesting. There are some other a more recent paper done by Giuseppe Magnifico, who is one of the guys who was also involved in this work, and now he's in Padova with Simone Montangero, who did the simulation for the same kind of things, actually for scattering of mesons in 2D. Okay, here we can talk about scattering of mesons, and they find a similar situation in which actually they have different regimes. And this is a very interesting, anyhow, question to answer. It would really be nice to see what happens. What seems to happen here that you don't really reach an asymptotic state in which you have free excitations, right? So everything stays confined here and in a very strong way. There is another thing that somehow struck me, because if I think it classically or semi-classically, I would think that the idea that you let the string evolve freely, so I would expect classically that at a certain point it will start breaking, okay, because the energy grows linearly in one dimension, right, with the size of the string. But classically, I would expect it to break it into half, and then in fourth, and so on, okay? Instead, what you see here, that quantum mechanically, it actually breaks immediately into the smallest strings as possible, so just meson pairs, okay? And then the fact that two mesons emerge at the end is just a result of interference effect that happens in the middle, at intermediate times. There's something also that struck me, but I have no physical intuition why that's happening actually.
The first picture reminds me of hadronization that people at QCD talk about. So
it could be, right? Right.
I know that this is not really, QCD, but nevertheless.
I just have intermediate small pairs, and then we just recombine them with the quantum. This is a really purely quantum interference effect, okay?
That's right.
And at the very end, you see the two mesons. So
that's why I was curious about the last picture, whether there's any intuitive and any physical understanding. But thanks.
Yeah, just saying that this is particle cannot actually move at all, right? And pair production is completely suppressed somehow, okay?
Well,
because what I see here is that actually have this string breaking mechanism. What happens is that I'm able to create particle-antiparticle pairs inside the string, and that they're eventually recombine somehow. Okay, and here this pair production is completely suppressed in the strong coupling regime.
Well, thank you very much, Elisa, for this nice talk. So let's thank again.
Thank you to you all, and I hope everything will be fine for you till the very end of the conference.
Well, we can.
Grazie, Elisa. It's okay. Grazie, Elisa. She's not hearing.
Sorry, I think I muted you for mistake.
Hi, everyone.
Hi.
May you see my desktop?
Yes, we can see your screen. It's fine.
Sorry?
It's fine. Yes, we can. Okay. We can see the screen. Great. So our next speaker is Professor Alessandro Zampini from Naples University, and he's going to talk about a Lagrangian description of Heisenberg and Landau von Neumann equations of motion.
Hi. First of all, let me let me thank you all for the nice opportunity to talk in this conference, and let me say that I'm very happy to be at this conference at whatever distance, and happy to give my contribution, and happy to, at the end, to say happy birthday to Bal on occasion of his birthday. So let me start. Let me start with my talk. I mean, you see what I write here. I mean, among the books that I started to study as an undergraduate, which means more or less 25 years ago, there are these two books which have been written by Bala, by Beppe Marmo, by Bostura Skjögastam, and by Alan Stern. These are the books on gauge symmetries and fiber bundles and classical topology and quantum states. Now, in these books, and these are books to which I periodically return, I read, among many other things, of course, these things that I list here. So I read about a geometric description of the dynamics of spin and spinless point particles, free and or coupled to monopole magnetic fields, and not to mention about Kaluza-Klein description of point dynamics. And other things I read on this book is about Lagrangians, which are defined on a tangent bundle of a Lie group manifold or on an orbit of the action of a Lie group on a manifold in terms of invariant forms. And above all, I mean, Lagrangians, which are affine linear in the velocity, which means affine linear in the fiber coordinates. And one of the other things I read in these books is how to write the corresponding equations of the motion via the Dirac theory of constraints, which is nowadays often referred to as the presymplectic constraint algorithm. And one of the things that I learned by reading these books is how to reduce the motion in terms of vector fields, in terms of of vector fields on a reduced space with a huge class of gauge symmetries. So the aim of this talk, the aim of my talk today, is to review a Lagrangian description for the dynamics of a finite level quantum system. And to do that, I will follow papers written by all these friends and colleagues. I mean, Florio Sciaglia, Fabio Di Cosmo, Antonio Figueroa, Alberto Ibort, Volo Diamanco, of course, Beppe, Luca Schiavone, Franco Ventriglia, and Patrizia Vitale, which are, at least the Italians here in this list are more members of what Beppe defined to be the Neapolitan part of the Italian family of Bal. And the reason why I decided to review this Lagrangian description is that many of the notions that I read in that books at that time are present in them, and many of the previous terms are among its keywords. So let me just begin with a kind of setting. We know that when we have a time evolution in terms of a position and the velocity of a system, we consider the tangent bundle of a smooth finite dimensional manifold, which we call the configuration space. And we know that this time evolution has a Lagrangian formulation if there is a Lagrangian function, which is a function with values in Rn defined on the tangent bundle of M, such that it corresponds to the stationary points of the action functional that we write traditionally in this way. Now, the variations with respect, we consider the variation problem must be suitable. By suitable, we mean that they must be, as I write here, second order variation, which means that the variation on the velocity, let me say, must be the time derivative of the variation on the position. Now, the Euler-Lagrange equations of the motion that we get are second order relations that we write in this way, and it's well known to every one of us. Now, if we consider that V dot is the acceleration of the system, of the point system, then we can write the equation, the Euler-Lagrange equation, in the blue way that I wrote here. So the first thing that we notice, after we have noticed that Euler-Lagrange equations are second order in time, we notice that Euler-Lagrange equations are implicit ordinary differential equation. Now, if the Lagrangian is regular, then the accelerations can be solved for, and the dynamics can be written in terms of a second-order vector field that I write here as this capital D. Now, from a more geometrical point of view, we can, geometrical in the sense that we can use it without using coordinates. Such equations can be written, such equation can be written, as I wrote here, in terms of the Lagrange one form theta L, which is defined by this expression, and in terms of its differential, which is the Lagrangian two forms, omega L, while the function E is the so-called Lagrangian energy. Now, we know that the Lagrangian is regular if the Euler-Lagrange equations have a symplectic formulation on Tm, which means that the two-form omega L is non-degenerate. A singular Lagrangian amounts to have a presymplectic system on Tm, and then we have a dynamical system that we have to analyze by the Dirac-Bergman constraint algorithm. Now, let me start by a Lagrangian description for the Schrödinger equation. That's the first time. So the first example we want to describe. So consider quantum dynamics on a finite dimensional Hilbert space C to the n. And we all know that the Schrödinger equation can be written in this way in terms of a self-adjoint, an Hermitian operator on this Hilbert space. Now, the two things that we want to notice is that the Schrödinger equation is both linear on H and first order in time. But moreover, since we know that pure states of a quantum system are given by rays in H, which means equivalence classes in the complex projective spaces given by H0, which means H without the null vector, quotiented by the action of non-zero complex numbers, and in particular, we describe this complex projective space as the basis of this principal bundle. The idea is to look for a Lagrangian on the tangent space of H0, whose Euler-Lagrange equations give solutions which are projectable on the projective space, which means we are looking for a time evolution for vectors in H0, which can be reduced to the projective space, to the basis of this bundle. Now, the first idea of a Lagrangian fulfilling these conditions was given by Dirac and Frenkel already in the 30s. And this Lagrangian, and a possible Lagrangian, is given in this way. Now, as we know, this Lagrangian, as we see in this example, this Lagrangian is linear in the velocities, okay? So it's not regular, it's a singular Lagrangian. Now, which kind of Euler-Lagrangian equation do we get? We get the equations that I wrote here in the blue color. Now, as we see, this doesn't appear to be the usual Schrödinger equation that we know and that we wrote on the previous slide. So we have to analyze some aspects of this equation. The first thing that we notice is that one can prove that if psi of t solves this equation, this blue equation, with any Cauchy datum psi 0, then if we define phi of t via psi of t times any complex non-zero number alpha of t, here alpha of t is a complex number, then phi of t solves the same equation with an initial datum given by, here is alpha 0 times psi. It's my mistake in writing, I'm sorry. So why can we, how do we prove it? This comes by noticing that after this multiplication, so the transformation from psi to phi, and phi is given from psi by multiplying it by a term which is a complex non-zero number, we see that the Lagrangian that we wrote here at the beginning of the slide gets transformed by a total derivative. And then we know that the equations of the motions are not changed by this gauge, so to say, gauge transformation, so-called gauge transformations on the Lagrangian. So this shows that the dynamics on H0, which is described by this evolution equation, projects onto a dynamics on the projective space. Now, notice that the Lagrangian L0 on the tangent space to H0 is not the pullback of a smooth Lagrangian on the tangent space to the projective space, to the quotient space. Why? Because this would correspond to a global gauge fixing on the principal bundle that we are considering. But we know that this principal bundle is not globally trivializable. A global gauge fixing would amount to a global section, which means to a global smooth function from the basis of the bundle to the total space of the bundle, which is the right inverse of the projection. And this is possible if and only if the principal bundle is trivializable. So this means that since this principal bundle is not trivializable, the Lagrangian cannot be the pullback of a smooth Lagrangian on the tangent bundle of the basis of the bundle, of the principal bundle that we are considering when we consider the rays of the quantum system. So in order to recover the Schrödinger equation on H0, the strategy is to lift horizontally to the total space of the bundle, which is H0, the dynamics on the basis of the bundle, on the quotient space, which means from the base to the total space, as I was saying. Now, how do we attain it? This is attained by a connection on the bundle whose integration gives a parallel transport map. So the parallel transport map that solves one of those that solve the problem is the one that I wrote here in blue color. As we see, phi of t is defined in this way with respect to psi, and this amounts to horizontally lifting psi to the total space of the bundle. One proves that phi is, of course, an element in H0, and that this phi solves the Schrödinger equation the way we know it. And moreover, the norm of the vector phi is the same norm of the vector psi. So this is about the Lagrangian description of the Schrödinger equation. And we know that in this description, in this Lagrangian description, we have used the keywords of, first order Lagrangian, reduction, lift, and, so to say, principal bundles and connection on it, which are the keywords of the books that I mentioned at the beginning of this talk. Now, let me go to a Lagrangian description of the Heisenberg dynamics, and let me start by what may appear as an unrelated problem with respect to ours. So let's consider gamma to be any Hamiltonian vector field defined on the exact symplectic manifold M. So now M is any manifold with a symplectic form omega, which is exact, which means that omega is given by minus, which is just a matter of convention, minus the exterior derivative of a potential 1-4. Which means that since gamma is Hamiltonian, this relation is the starting point of our analysis. If we write this relation locally, we have x for the vector field and theta for the one forms, for the potential one form. So we know that this relation here can be written in the blue color here, as I wrote here. Now the question we wonder is, although not of second order, because clearly on M, this vector field gamma gives us a first order equation of the mode, a first order ODE, ordinary differential equation. So may we describe this first order ODE as a suitable system, maybe of a singular implicit equation of Lagrangian type? So this is the question we want to address now. And in order to answer to this question, we simply consider not M, but M as the basis of its tangent bundle. So we have local coordinates X and V, and now we can define a Lagrangian function on the tangent bundle to M. And we define the Lagrangian function in this way, where H is exactly the Hamiltonian function of the vector field gamma that we wrote before, and theta is the potential of the symplectic two-form that we have considered on M. Now, with this definition of the Lagrangian, one computes the Lagrangian one form, and one sees that the symplectic, that the Lagrangian two form is not symplectic on Tm, and the problem can be written by these two lines here. Now we see that omega L has a huge kernel, and the kernel of omega L coincides with the set of all vertical vector field on Tm. So in some sense, this is a kind of limit case for the constraint algorithm, because the kernel of the of the Lagrangian two form is so huge that the reduction via the Dirac-Bergman algorithm gives that since omega is non-degenerate on M, one can extract the V coordinate here from the first equation here in blue color. And so one has these two conditions, which means that so now the vector field gamma comes as a reduction to M of the implicit Euler-Lagrange equations on Tm for the given singular Lagrangian. And the given singular Lagrangian is the L functions that I wrote here at the beginning of the slide. So why is this example interesting for us within this talk? Because an example of such a reduction comes from the dynamics of a finite level quantum system. So our Hilbert space now is still C to the n, and the infinitesimal evolution of any observable, which means any Hermitian operator on H, is given by the Heisenberg equations of the motion that are written in terms of the commutator between these two operator H, which is the Hamiltonian, and A, which is the observable, which is evolving in time. So we see that this dynamics is linear on the real vector space A, which is the realification of the vector space given by the space of Hermitian operators on H. Okay. Now, since this vector space has n2, n squared, sorry, dimension, we know that this is a real vector space isomorphic to R to the n squared. Now, this vector space is in general not even dimensional. So the possibility of a Hamiltonian description is in principle not allowed. So one first explores the possibility of describing such a dynamics within a Poisson formalism. In order to get that, we consider the map that associate to any Hermitian operator its anti-Hermitian, so to say, brother, given by multiplying A times the imaginary unit. So this map is a real vector space isomorphism between the set A of Hermitian and the set A tilde of anti-Hermitian linear operators on the Hilbert space H that we are considering. Now, the important step is to notice that A is not a Lie algebra, but A tilde is the Lie algebra, is isomorphic to the Lie algebra of the unitary group in n dimension. So under this isomorphism, the equations of the motion can be written in this way. And now we have to recall that the vector space of the matrices on H, so of bounded operators on H, is itself a Hilbert space with respect to this scalar product, which is given by the finite dimensional version of the Hilbert-Schmidt norm on the space of bounded operators on a Hilbert space. So with respect to this Hermitian scalar product, we have an orthonormal basis for our vector space A tilde, and we may define them as this matrix TOEs. Now, of course, since we have a basis and we are on a finite dimensional vector space, the components of A tilde, of any A tilde with respect to this basis, gives a system of global coordinates. And moreover, we know that since A tilde is a Lie algebra, it means that we have this structure constants when we consider the commutator of two elements of the basis. So now, since UN is a Lie algebra, we can consider a finite dimensional Lie algebra in particular, we can consider its dual. And on its dual, we can consider a basis, which is dual, the basis epsilon, which is dual to basis tau. So it means that we can identify the elements tau as linear functions on the dual. And so we may define, we can identify any element in A tilde with a linear function on the dual of the Lie algebra. So we can write this expression that we have written many times and we have read many times in many of our papers. And this expression, which means I'm considering the commutator, and since the analogy between the commutator of two matrices and the Poisson bracket of functions, we are inducing a Poisson bracket on linear functions on the dual of a vector of the Lie algebra that we are considering, which is the vector space A tilde. So now this expression, as we know, can be extended to all smooth functions on the dual, and since the dual and UN can be identified in terms of the scalar product, it means that we can define a Poisson bracket on functions on A tilde and on A, since they are isomorphic. So we then say that the Heisenberg dynamics has a Poisson formulation. Now, since we want to have an Hamiltonian description for it, we consider that the space of bounded operators of matrices here is this complex vector space and can be realified. So we have this decomposition in terms of two real vector spaces, A and A tilde, as we have already saw. And along a basis, it means that any element has both coordinate x and coordinates y with respect to the basis sigma j, and the coordinates are given by the action, of course, of the scalar product. Now, the set x and y give a global set of coordinate system for the set of for this vector space. Now, since B of h is a vector space, is a real vector space, we can identify the tangent space with itself, and the Hermitian product induces a Euclidean metric and a symplectic structure that along these coordinates can be written in the way here of the last blue expression that I wrote in this slide. So the real part gives us a metric, and the imaginary part gives a symplectic tensor. And moreover, one has another tensor, which is this one here, and this is the complex structure, and it's comparable with both the Euclidean structure and the symplectic one, and these three lines here shows the compatibility. It means that on the set of operators on H, we have a Kähler structure. Now, we know that the quantum evolution is linear, as we know, and is Hermitian, which means that it preserves both the Euclidean and the symplectic tensors. Now, if the Hamiltonian has coordinate HA with respect to the basis we have considered, it means that the evolution, the quantum evolution on B of H can be written in terms of x dot and y dot, and is linear with respect, as we wrote here. Now, the vector field that is describing such a dynamics is linear, and its Hamiltonian can be written as a quadratic function, which means x and y, as we said. And the indices here, okay, have been, lowered by the Euclidean structure that we have. So, looking at the previous slide and comparing it with this analysis, we see that both A and A tilde, which means the subset of Hermitian and the subset of entire Hermitian operators, are Lagrangian submanifold of BH with respect to the symplectic structure that we are considering. And quantum dynamics, which is Hermitian, projects onto both submanifolds. So it means that if we consider this projection associated to the direct sum decomposition, one has that the push forward of gamma exists on A, which is the set of Hermitian operator on our space, and describes the Heisenberg dynamics as a reduction of the Hamiltonian dynamics gamma on the unfolding symplectic space, which is given by B with omega. So now it takes another little step to recover that since the dynamics gamma on B has a Lagrangian formulation on the tangent bundle to B, we have that this Lagrangian, following the example I was describing you, 5 minutes ago, this Lagrangian can be written in this way. So as we see, this Lagrangian is a fine linear in the velocity. Here is x dot, here we have y dot, and there's a potential term which is given by the Hamiltonian function. Now, notice that such a Lagrangian vanishes on both A and A tilde. And this is perhaps more evident if we parameterize the real manifold of matrices on Cn in terms of matrices A and A dagger, since it gives this expression here. And here it's clear that on both Hermitian and or anti-Hermitian matrices, this Lagrangian vanishes. Now, the corresponding equations of the motion on T of BH can be reduced to the basis of the bundle and coincide with the Heisenberg equation. One can directly compute the Lagrangian 1 form, which has this expression, and the Lagrangian 2 form, which is the up to a sign, the differential of theta L, which has this expression. And the Euler-Lagrange equation can be written, as we know, geometrically, intrinsically, in this way, and an explicit computation gives us this expression. Now, since dA and dA dagger are independent, and the second step is that H is Hermitian, the vanishing of this expression gives exactly that both here coefficients must vanish, and they are one the adjoint of the other, and they are exactly the Heisenberg condition. So let me go one step further now, and let us notice that if we consider a smooth map phi between a manifold S and our manifold M, now any smooth function f on Tm can be pulled back to a smooth function f prime via this procedure, as we all know. Now, this means that if we have a Lagrangian function on Tm, then we can induce a Lagrangian L prime on Ts, and therefore an implicit possibly singular, of course, possibly singular, because we don't know how S is embedded, for example, into M, or we don't know the specific of the maps phi with respect to M starting from S. So a possible idea is that starting from a Lagrangian dynamics on Tm, we can study how to induce a Lagrangian dynamics with a function L prime on Ts.
Alexander,
now,
excuse me, you still have 10 minutes.
Please. Yeah. Now, I want you to notice that this is not the strategy we adopted in order to provide the Lagrangian for the Heisenberg equations on the Hermitian matrices, on the space of Hermitian matrices A, since L vanishes on A. what we did before is that we unfolded A into B of H, we found a Lagrangian description on B of H, and then reduced the dynamics, which means what we call the vector field gamma, to A. Now, the idea is that, inspired by the parametric information theory, why? Simply because the focus in that setting is on parameterized family of elements of the algebra B of H, one can induce a dynamics on a suitable submanifold in B of H. So the idea is, consider an element A naught. A naught here is any element in B of H, and consider the left action of a Lie group G on B of H, so that we have an orbit. So now S for us is the orbit of this action, is the left orbit of this action. Since S is embedded into B of H, one can define a Lagrangian on S via pulling back the Lagrangian L from T of BH to T of S via this recipe. And this result in this Lagrangian that I wrote here in blue. Now, what I want you to notice is that this Lagrangian depends on G dot G to the minus 1, which is one of the key things that I read on that books, and which give a way to study the dynamics on the tangent bundle of a Lie group in terms of its Lie algebra. Now, this Lagrangian, as one can prove directly, has a kinetic term which is linear in actually the skew symmetric part. This is due to the fact that G is not necessarily a unitary action, okay? So the Lagrangian has a kinetic term which is linear in the skew symmetric part of the G dot G to the minus 1 term on the tangent bundle of a G orbit. So one can apply the theories we studied in the books we started from. And we know that the infinitesimal symmetries of the kinetic term are related to the kernel of the Lagrangian 2 form. So the infinitesimal symmetries of the kinetic terms give us the first step of the Dirac-Bergman reduction procedure. Now, in the rest of the slide, there are just computations to show you what exactly the Euler-Lagrange equations look like, but they are not so interesting to me, at least, as the points that I was driving you. So let me go to the last comment here. Although induced from a linear dynamics on BH, because don't forget that we are considering the quantum linear evolution on BH, which is linear. So although induced from a linear dynamics, this dynamics is nonlinear. Moreover, the Lagrangian is singular, and therefore the Euler-Lagrange equations are implicit and can give rise to constraint analysis, which can be performed explicitly in specific examples. And this is something that actually I already told you. So what about the Landau von Neumann equations? And these are the last slides of my presentation. Okay, let me start just by recalling that the Landau von Neumann equations are this one. So rho dot is equal to I commutator, I times the commutator rho h. And these equations are the infinitesimal version of the unitary dynamical evolution given by the conjugation on a state rho. We are considering finite levels, so it means that any rho is represented by a density matrix, which means that rho is self-adjoint, positive, and trace 1, while, of course, the evolution is given by the time exponential of the I times the Hamiltonian. So the first idea for a Lagrangian description of the Landau equations seems to consider that since the set of states can be represented by density operators, and density operators are represented in terms of matrices on H, then one can define a Lagrangian on T of D on the tangent bundle to the set of density matrices via the strategy, via the pullback of the embedding. Okay. Now, given the Lagrangian that we had before, one immediately notices that the Lagrangian, so to say, embedded Lagrangian vanishes, simply because D is a subset of A. The elements in D are self-adjoint. So, of course, the Lagrangian vanishes when it's pulled back via the same strategy that we already used before. Now, the key observation is that the dynamical evolution, the key observation to solve this problem, is that the dynamical evolution of a state, of any state sigma, takes place on the manifold of states which are isospectral back to sigma, and that such a space is the quotient of the orbit for the action of the unitary group, and the action is given by conjugation here. So, of course, this manifold O sigma is the quotient of the unitary group via, so the quotient is given by U of H modulus the isotropy subgroup, of course, of this action. Now, the immersion of O sigma within B of H is such that, again, the induced Lagrangian vanishes on it once more, because also U dagger sigma U is a self-adjoint element. So consider now at least the solution that we found studying this problem is that we can consider this map now. We have the state sigma and we have unitary elements U. This map amounts to provide for a positive Hermitian operator a kind of module and a phase, which is given by the unitary factor, and therefore can be seen, at least intuitively, as an operatorial square root for the state rho. Via this map, one can consider this embedding, and via this embedding, one can induce from L a Lagrangian on the manifold O sigma that we wrote. Now, this Lagrangian doesn't vanish, and this Lagrangian again shows a kinetic term depending on the unitary Lie algebra term, which is U dot U dagger, which means since now U is unitary, U dot U to the minus 1. Now, in order to derive the Euler-Lagrange equation, one has to do some computations. In the Lagrangian one form, one sees that the right invariant Moret-Cartan form appears, the Moret-Cartan form with respect, the Moret-Cartan form corresponding to the unitary group action UH on BH. So the right invariant Moret-Cartan form appears, and some other calculation allows to write the blue expression here, which are exactly the the Euler-Lagrange equations. Now, the left invariant Moret-Cartan form appear, which is U to the minus 1 du, and one can embed this expression into the blue expression, and one has here the crucial last formula relation. Since we are considering the trace of this expression with respect to the left invariant Moret-Cartan form, since the trace operation with respect to the Moret-Cartan form amounts to consider the independent coefficients of an element with respect to a basis of left invariant forms, one gets that the terms here in round brackets should vanish. So we get exactly the Landau von Neumann equation. So let me just conclude by mentioning that I hope I have described in enough clarity how it is possible to formulate the quantum dynamical evolution of a finite level system, both in the Schrödinger, the Heisenberg, and the Landau von Neumann formalism, although they are written in terms of first order equations and within the Lagrangian setting using the properties of fiber bundle and the notion of reduction. Now, the most of this material comes from the papers I am quoting here, but actually what is interesting, what is important to me now is to thank you all for your kind attention, and most important is to say tanti auguri, Bala, buon compleanno, è un piacere, è un onore essere stato un tuo studente a Syracuse e soprattutto il fatto che possa parlare con te in italiano. Grazie.
Ciao Alessandro.
Grazie.
Come stai? Tutto bene? Molto tempo che
Benissimo,
hai
e
visto.
guarda, since I'm using Italian, also my mother wishes you happy birthday.
Okay, thank you. Till next time.
Okay, thank you very much, Alessandro, for this nice talk. So, do we have questions or comments?
Fedele.
Yes, may I? Okay, talking about birthdays, happy birthday, Alessandro. I have insider information. If you go back to page 6, there is one comment something I would like to understand. The equation, the first blue equation, this is only makes sense only in finite dimensional in the finite dimensional case, because in the infinite dimensional case you are saying that a vector in the Hilbert space, if H belongs to the domain, if psi belongs to the domain of H, you're saying that a vector is proportional to identity, so it can only be if it's zero, both sides.
Dirac and Frankel says it's valid at infinite dimension, but what I'm writing here is, mathematically right only in finite dimension. Yes.
But it has also no content.
It's not valid. It's not valid if psi is zero. Yeah.
No, it's not. It has no content. It's the same information as the Schrödinger equation.
Yeah.
Because it brings H psi to the left. So you are saying that the Schrödinger equation, which is a vector in the Hilbert space, is equal to a number on the right. So if it's a number is a multiple of the identity,
right.
doesn't
You're
belong
right.
to the Hilbert space. So it's just saying that ID over dt of psi minus.
I wasn't noticing that there is a mistake in writing here. There is a psi missing.
Okay. Okay, then it's an eigenvalue. Okay, if a psi is missing, then my objection doesn't hold. Okay, sorry.
No, I'm sorry.
Okay.
Thanks for pointing it.
Okay. I would have a question regarding the geometric treatment of density matrices now in the last part of the talk. So, there is this generalization of Berry's phase to density matrices, no? Some people call it Ullmann's phase, but more people have worked on it. So I wonder, now the point is that there are different possibilities to define a parallel transport when you lift density matrices to Hilbert-Schmidt operators. So I wonder if it is possible within your formalism to say something about this type of parallel transport.
Maybe, but I have not a complete answer to your question. It might be, okay. But it's something I haven't thought about. So I'm not sure I can give you a complete answer, but it's something I can think of. We can think of. Thanks for the question, actually. Okay, but I'm sorry.
No, great.
I'm not able to.
Okay,
to provide you a complete answer.
Right, thank you. Well, if not, if there are no more questions, then let's thank again Alessandro for his talk.
Thanks to you.
Thank you very much. So now let me give a small announcement. We will have a coffee break now. There has been a slight change in the program, so we will meet again at 4:30 for the public talk. Thank you.
Sorry, I have one more announcement about tomorrow's program. Tomorrow's program will be at IIT Chennai. So there will be a bus arranged at 9 a.m. from IMSC to IIT tomorrow. So please be here by 9, and I'll see you tomorrow morning.
Sorry, did I understand well? You reconvene at 4:30
yes.
Indian time, so Giorgio's talk is cancelled?
Yes, for now, yes. That's correct.
Okay.
Okay.
Okay, thank you.
Oh, he's directly giving.
How you have?
No break. Going on there, no? Yeah. இந்த ஸ்ட்ரீமை கட் பண்ணிடுறேன் அப்படின்னா. அடுத்த ஸ்ட்ரீம் புதுசு தானே.